The first black hole in the universe did not come from a dying star. It couldn't have. Because when it formed, stars didn't exist yet. Galaxies didn't exist. Atoms barely existed. The entire cosmos was less than 1 second old, a screaming inferno of light and particles expanding faster than anything physics should allow. And somewhere in that chaos, gravity found a way to win. Not later, not after billions of years of stellar evolution and supernova collapse. Right then, in the first breath of creation itself, we call them primordial black holes. Stephen Hawking proposed them in 1971, and for decades they lived comfortably in the pages of theoretical journals, a mathematical curiosity with no real evidence and no pressing reason to take them seriously. Then astronomers started finding things they couldn't explain. Supermassive black holes sitting at the edge of time, just 690 million years after the Big Bang, already weighing 800 million times the mass of our Sun. Monsters that had no right to exist. Not that early, not that massive, not unless something gave them a head start. And that's when primordial black holes stopped being a curiosity and became a solution. Because if black holes could form in the first second, directly from the density ripples left behind by cosmic inflation, then they wouldn't need stars, they wouldn't need time. They would simply be there, waiting in the dark, seeding the first galaxies, shaping the structure of everything that came after. Some scientists go further. They suggest these ancient survivors might be the dark matter we've been searching for, the missing mass, the invisible scaffold holding the universe together, not exotic particles, just black holes, older than light itself. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across the abyss of early time, we will reconstruct the conditions, weigh the competing stories, and confront what remains unknowable. The answer may not have a name, but the path toward it begins where the universe kept its deepest secrets. There is a moment in the history of the universe where every rule we know stops working. A fraction of a second so brief that your brain cannot hold it. A temperature so high that matter as we understand it cannot exist. A density so extreme that space itself might as well have been boiled down to a single point. And in that moment, 13.8 billion years ago, everything you have ever seen, touched, or measured was packed into a volume smaller than a grain of sand. This is not poetry. This is physics. The universe began in an event we have somewhat awkwardly named the Big Bang. And despite what the name suggests, it was not an explosion in space. It was an explosion of space. Space itself, time itself, matter and energy, and every dimension you can point to, all of it erupting into existence from conditions so alien that the equations we use to describe reality simply break down when you try to push them backward past that first instant. For the first fraction of a second, a span of time measured in units like 10 to the power of -36 seconds, the universe underwent something called cosmic inflation. This was not gentle. This was not gradual. The entire observable universe, every galaxy cluster, every star, every atom that would one day become you, inflated from a region smaller than a proton to something the size of a grapefruit in less time than it takes light to cross the nucleus of an atom. Then it kept expanding, though at a slightly less hysterical pace, at roughly 1 second after the Big Bang, and this is the point where we actually have decent physics to describe what was happening. The universe was still unimaginably hot. Estimates put the temperature at around 10 billion degrees Celsius. That is 18 billion degrees Fahrenheit for anyone keeping track, though at that scale, the difference between units stops mattering. You are talking about an environment where particles are slamming into each other with so much energy that they cannot settle into anything stable. Electrons, protons, neutrons, photons, neutrinos, all of it mixing in a kind of high-energy chaos that NASA has politely described as a primordial soup. That soup was opaque. Light could not travel more than a tiny distance before smacking into another particle. If you could somehow stand in the universe at that moment, which you could not, because you would be instantly vaporized, and also because there was no standing in any meaningful sense, you would see nothing. Not darkness, not light, just an impenetrable fog of radiation and matter, so tightly coupled that the two were functionally the same thing. The universe kept expanding, the temperature kept dropping, and as it cooled, the first stable structures began to form. During the first few minutes, a process called Big Bang nucleosynthesis kicked in. Protons and neutrons, no longer being smashed apart by the ambient heat, started sticking together to form the nuclei of the lightest elements. Hydrogen first, then helium, with trace amounts of lithium and beryllium tagging along for the ride. That was it. No carbon, no oxygen, no iron, none of the heavier elements that stars would spend billions of years cooking up. Just hydrogen and helium, the simplest possible building blocks, and even those were not yet atoms. They were bare nuclei floating in a sea of free electrons. For the next 380,000 years, the universe remained a glowing fog, hot enough that electrons could not bind to nuclei, hot enough that photons could not travel freely. This period is sometimes called the Dark Ages, though that name is misleading because the universe was not dark. It was filled with light. You just could not see through it. Then, at around 380,000 years after the Big Bang, the temperature dropped below a critical threshold. Electrons finally settled into orbit around hydrogen and helium nuclei, forming the first stable atoms. This event is called recombination, another slightly misleading term because the electrons were not recombining with anything. They had never been combined in the first place, but the name stuck. The moment atoms formed, the universe became transparent. Photons that had been bouncing endlessly from particle to particle were suddenly free to travel in straight lines. The fog lifted, and the light that was released in that moment, stretched and cooled by billions of years of cosmic expansion, is still washing over us today. We call it the cosmic microwave background, and it is the oldest light we can observe. A faint radio hiss left over from the moment the universe first opened its eyes. But here is what matters for the story we are about to tell. At the moment the cosmic microwave background was released, the universe was still featureless. There were no stars, there were no galaxies, there were no black holes. There was just hydrogen and helium gas drifting through expanding space, cooling, thinning, waiting for gravity to pull it into something interesting. The first stars would not ignite for another 100 to 200 million years. That stretch of time, from recombination to the first starlight, is the true cosmic dark ages. A universe filled with matter, filled with potential, but producing no light of its own. Just neutral gas suspended in the dark, slowly clumping together under the patient pull of gravity. Eventually, those clumps grew dense enough to collapse. Gas clouds contracted, heated up, and in their cores, hydrogen nuclei began slamming together hard enough to fuse into helium. That fusion released energy. That energy pushed back against gravity. And when the two forces balanced, you had a star. The first generation of stars, called population 3 stars, were likely enormous, hundreds of times more massive than our sun, burning blue and furiously hot, living fast and dying young in supernova explosions that seeded the cosmos with the first heavy elements. And when the most massive of those stars exhausted their fuel, their cores collapsed. The outer layers blew off in a violent explosion. but the core kept falling inward, compressed by its own gravity into a region so dense that not even light could escape. A black hole, that is the standard story. Black holes are the remnants of dead stars. They are the endpoint of stellar evolution for the heaviest objects in the universe. You need a star first, a big one, and then you need that star to die in a very specific way. That story works beautifully for black holes we observe today. We have seen stellar mass black holes, objects weighing a few to a few dozen times the mass of the Sun, orbiting companion stars, feeding on their material, occasionally flaring up as X-rays when the infalling gas gets hot enough to scream. We understand those. We have the physics. We have the observations. The math checks out. But then you look back at the early universe and the story starts to wobble, because we have also observed supermassive black holes, monsters weighing millions or even billions of times the mass of the Sun, sitting at the centers of galaxies. And some of those black holes, the ones we have spotted with telescopes like the James Webb Space Telescope, existed less than 1 billion years after the Big Bang. In some cases, less than 700 million years. That is a problem. A stellar mass black hole that feeds at the maximum rate allowed by physics, a rate called the Eddington limit, still takes tens of millions of years to double its mass. Run the numbers forward, and you cannot grow a 1 billion solar mass black hole from a single dead star in the time available. There simply are not enough doubling periods between the first stars and the observations we are making of these early supermassive monsters. So either black holes in the early universe were growing much faster than the Eddington limit allows, which would require new physics or conditions we do not fully understand, or they did not start small. Maybe the seeds were bigger. Maybe some black holes did not form from stars at all. That possibility, the idea that black holes could form in the early universe without stars, without collapse, without any of the machinery we usually rely on, is where things get strange, and it is the gap where an old, somewhat fringe idea has recently started to creep back into the mainstream. The early universe was not smooth. Inflation stretched it flat on the largest scales, but at smaller scales, quantum fluctuations left tiny density variations in the primordial soup. Most of those variations were too small to matter. Gravity pulled on them, but they dissipated or got smoothed out by radiation pressure. But if, and this is the critical if, some regions were dense enough, if the fluctuations were sharp enough and concentrated enough, gravity could have won immediately. A dense enough patch of space in the first fraction of a second after the Big Bang could have collapsed directly into a black hole. Not from a star, not from a cloud of gas that took millions of years to contract, just from the sheer overdensity of the early universe itself. Gravity crushing a region of space-time so hard that it formed an event horizon before the universe had even finished its first second. These hypothetical objects are called primordial black holes, and if they exist, they would have formed before atoms, before nucleosynthesis, before the universe cooled enough for anything we recognize as matter to take shape. They would be relics of the Big Bang itself, fossils from a moment when the rules were different. The idea is not new. It has been floating around in theoretical physics since the 1970s, mostly ignored or dismissed as a curiosity. But in the last decade, as observations of the early universe have gotten sharper and the mysteries have piled up, primordial black holes have been dusted off and re-examined. Because if they are real, they solve more than one problem at once. They could explain how supermassive black holes grew so large, so fast. They could account for some or all of the dark matter that makes up 85% of the matter in the universe, but has never been directly detected. They could be the seeds that jump-started galaxy formation, pulling in gas and dust, anchoring the structures that would eventually become the cosmic web. But we are getting ahead of ourselves. Because before we can talk about what primordial black holes might have done, we need to understand how they could have formed in the first place. And that requires stepping into a universe that existed before stars, before light, before anything solid or stable. A universe where the only thing you had to work with was heat, density, and the relentless expansion of space itself. There is a strange tension at the heart of this story. We know more about the first second of the universe than we know about, say, the formation of our own moon. We can describe the temperature, the particle interactions, the evolution of the cosmos from 10 to the power of -12 seconds onward with startling precision. The equations work, the predictions match observations, the cosmic microwave background is a near-perfect fit to the models. And yet we are standing here, 13.8 billion years later, staring at black holes that should not exist, galaxies that assembled too quickly, structures that formed before the standard timeline says they had any right to. Somewhere in that first second, or that first minute, or that first few 100,000 years, something happened that we have not accounted for. A process we missed, a detail we overlooked. The universe did not wait for stars to build its first black holes. It might have made them in the fire of its own birth, stamped them out in the chaos before anything else had time to cool and settle. And if that is true, then the objects we have been calling the remnants of dead stars might actually be older than stars themselves. That would make primordial black holes the first permanent structures in the universe, the first things with boundaries, with mass, with gravity strong enough to warp space around them. Everything else, every star, every planet, every galaxy would come later. But the black holes would already be there, waiting in the dark, older than light itself. We do not know if this happened. We do not even know if it could have happened. But the math says maybe. The observations say something is missing. And the gap between what we expect and what we see keeps getting wider every time we point a more sensitive telescope at the early universe. Stephen Hawking spent years thinking about this problem, not because he was trying to solve the mystery of supermassive black holes. He was working on something else entirely, something stranger, a theory that predicted black holes should evaporate. And in the process of working through that theory, he realized that tiny black holes, ones far smaller than anything you could make from a star, could have formed in the first moments after the Big Bang, not as a quirk, not as an accident, but as a natural consequence of the extreme conditions in the early universe. Hawking did not call them primordial black holes at first. He called them mini black holes, and he predicted that the smallest ones should have already evaporated by now, their mass radiated away as a faint quantum hiss. But the larger ones, the ones that formed with enough mass to survive billions of years, those should still be out there, invisible, undetectable by most of our instruments, woven into the fabric of the cosmos like silent anchors holding the universe together. Nobody took him seriously. Not at first. Stephen Hawking's 1971 paper proposing that black holes could have formed in the first fraction of a second after the Big Bang landed in a field that was still trying to wrap its head around the idea that black holes could form at all. General relativity had predicted them decades earlier, but for most of the 20th century, black holes were treated as mathematical curiosities, exotic solutions to Einstein's equations that probably didn't correspond to anything real. The term black hole itself wasn't even coined until 1967 by physicist John Wheeler, and even then, many scientists assumed they were too strange, too extreme to actually exist in nature. Hawking was 29 years old when he published his paper on primordial black holes. He was already well known in theoretical physics circles, already making waves with his work on singularities and the physics of the early universe. But this idea, this suggestion that black holes could form without stars, was a step further out than most of his colleagues were willing to follow. The standard story of black hole formation was tidy. A massive star exhausts its fuel, its core collapses, and if the core is heavy enough, it punches through every known force of resistance and becomes a black hole. Clean, observable, rooted in processes we could see happening in the sky. Hawking's primordial black holes had none of that. They required no stars. They required no supernovae. They required nothing but gravity, density, and the chaotic conditions of the universe in its infancy. To many physicists, it sounded less like science and more like speculation. Interesting maybe, but untestable, unfalsifiable. The kind of idea you entertain at a conference dinner and then forget about when you get back to work. Hawking didn't forget about it, and neither, as it turns out, did the universe. The idea of primordial black holes didn't originate entirely with Hawking, though he is the one who developed it into a rigorous theory. The first hints came from Soviet physicists Yakov Zeldovich and Igor Novikov in 1966 and 1967. They had been thinking about the early universe and realized that if the density of matter varied enough from place to place, some regions might collapse under their own gravity before the expanding universe could smooth them out. They sketched the basics, noted it as a possibility, and moved on. Hawking picked up the thread a few years later and turned it into something you could calculate. The core insight is deceptively simple. In the first moments after the Big Bang, the universe was not perfectly smooth. Inflation had stretched space flat on the largest scales, but at smaller scales, quantum fluctuations left tiny wrinkles in the density of the primordial plasma. Most of those wrinkles were harmless. They stretched and faded as the universe expanded. But if a wrinkle was sharp enough, if the density in a particular patch of space exceeded a critical threshold, gravity could lock onto it and pull it inward faster than the expansion could pull it apart. The threshold is usually described in terms of a density contrast, a measure of how much denser a given region is compared to the average density of the surrounding universe. The rough number that keeps showing up in the literature is about 10%. If a region's density was 10% or more above the background, and if that overdensity was concentrated in a small enough volume, it could collapse. Not slowly, over millions of years like a gas cloud forming a star, immediately, gravitationally. A runaway collapse that would not stop until the region had crushed itself into a singularity and wrapped an event horizon around the result. That event horizon is what makes it a black hole. And because the collapse happened in the early universe, long before the first stars ignited, these black holes would not be constrained by the usual mass limits. Stellar black holes form from stars, so they inherit the mass range of stars. Roughly a few solar masses on the low end, up to maybe 100 solar masses for the most extreme cases. Primordial black holes had no such restriction. They could form at whatever mass the density fluctuation happened to contain. Too small, and they would evaporate almost instantly through a process Hawking himself would later describe. Too large, and they might be indistinguishable from the supermassive black holes we see today. But in between, across a staggering range of possible masses, you could have black holes that formed before atoms existed. The smallest primordial black holes theoretically could have masses down near the Planck scale, around 10 to the power of -8 kilograms. That is roughly the mass of a large bacterium compressed into a region smaller than a proton. A black hole that small would not last. Hawking's later work on black hole thermodynamics showed that black holes radiate energy, and the smaller the black hole, the faster it radiates. A Planck mass black hole would evaporate in less than 10 to the power of -40 seconds, a timescale so brief that calling it instantaneous would be generous. But scale up just a bit, and things get more interesting. A primordial black hole with a mass of around 10 to the power of 12 kilograms, roughly the mass of a small mountain, would have a lifetime comparable to the current age of the universe. Anything more massive than that, and the black hole would still be around today, quietly surviving in the dark, radiating so slowly that it might as well be eternal. Go larger still, and you get primordial black holes with masses comparable to asteroids, planets, even stars. These would be indistinguishable from stellar black holes in terms of their gravitational behavior, but their origin story would be completely different. They would not have formed from the death of a star. They would have formed before the first star was born, stamped out in the violence of the Big Bang, like coins minted in the first breath of creation. The timing matters. Primordial black holes are thought to have formed in the first second after the Big Bang, possibly earlier, during the inflationary epoch, though that depends on the details of how inflation ended and how quickly the density fluctuations froze into place. By the time the universe was a few seconds old, the window had closed. The density had dropped too low. The expansion had smoothed things out. Any black holes that were going to form from primordial density peaks had already formed. That makes them older than everything else. Older than hydrogen atoms, older than nuclear synthesis, older than the cosmic microwave background. If you want to find the first permanent structures in the universe, the first objects with boundaries and mass and gravity strong enough to hold themselves together against the expansion of space, primordial black holes are the only candidates. Hawking understood that this idea was strange. He also understood that it was testable, at least in principle. If primordial black holes existed, they would leave marks, not dramatic ones. You would not see them glowing in the sky, but they would interact with matter. They would bend light. They would contribute to the overall mass budget of the universe. And the smallest ones, the ones light enough to evaporate within the age of the universe, would produce a faint signature of radiation as they disappeared. That radiation, now called Hawking radiation, became one of the most famous predictions in modern physics. It arises from quantum effects near the event horizon. In empty space, particle-antiparticle pairs constantly pop into existence and annihilate each other almost immediately. Normally, this process has no lasting effect, but near a black hole's event horizon, one member of the pair can fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting particles. The energy for those particles has to come from somewhere, and the only place it can come from is the black hole's mass. So, over time, the black hole loses mass. It evaporates. For a large black hole, this process is absurdly slow. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But a small primordial black hole, one with a mass around 10 to the power of 12 kilograms, would be radiating much more aggressively. It would glow faintly in gamma rays as it approached the end of its life, and then it would vanish in a brief flash of radiation. No one has ever detected that flash. Searches have been conducted, looking for unexplained gamma ray bursts that might match the signature of an evaporating primordial black hole. So far, nothing. That does not mean they are not out there. It just means that if they exist, they are either very rare or the ones small enough to evaporate have already done so in regions of space we have not been watching. The larger primordial black holes, the ones that would still be around today, are even harder to detect. They do not radiate significantly. They do not glow. If one passed through the solar system, we might not notice it at all unless it happened to pass close enough to a planet or the Sun to produce a measurable gravitational disturbance. A primordial black hole with the mass of an asteroid would have an event horizon smaller than an atom. It could pass through the Earth, through your body, through a star, and the odds of it actually hitting anything on the way through would be vanishingly small. It would interact gravitationally, bending space around it, pulling slightly on nearby matter. But its physical cross-section would be so tiny that it would slip through solid matter like a needle through fog. One paper described the effect of a primordial black hole passing through a star as being like a bullet. It would carve a narrow tunnel, heat the material along its path, and exit the other side. The star would barely notice. If the black hole was small enough and moving fast enough, the encounter might leave no lasting trace at all. That invisibility is part of what makes primordial black holes so compelling as a dark matter candidate. Dark matter is the name we have given to the 85% of the matter in the universe that does not emit, absorb, or reflect light. We know it is there because we can see its gravitational effects. Galaxies rotate faster than they should, based on the visible matter alone. Galaxy clusters hold together more tightly than the stars and gas within them can account for. The cosmic microwave background shows patterns that only make sense if there was extra mass pulling on the early universe's density fluctuations. For decades, physicists assumed dark matter was made of some exotic particle. Weakly interacting massive particles, or WIMPs, were the leading candidate for a long time. Experiments were built to detect them. Deep underground detectors, satellite observatories, particle colliders, billions of dollars and decades of work. And despite all of that effort, no one has ever directly detected a dark matter particle. The detectors have come up empty. Primordial black holes offer an alternative. If a significant fraction of the dark matter in the universe is actually made up of black holes, ones that formed in the early universe and have been drifting through space ever since, that would explain the gravitational effects without requiring any new particles. Black holes are made of ordinary matter, or at least they were before they collapsed. You do not need to invent new physics. You just need the early universe to have been lumpier than we thought. The idea is not without problems. If primordial black holes made up all of the dark matter, we should see more gravitational lensing events than we do. When a black hole passes between us and a distant star, the black hole's gravity bends the star's light, causing the star to briefly brighten. Surveys have looked for these micro-lensing events in the Milky Way and in nearby galaxies. They have found some, but not enough to account for all the dark matter. That suggests that if primordial black holes exist, they can only make up a fraction of the dark matter budget, maybe 10%, maybe less. Or maybe they are out there, in a mass range we have not been able to constrain yet. The observational limits are patchy. We have decent constraints on primordial black holes in certain mass ranges, but there are gaps. Windows where a population of primordial black holes could be hiding without violating any of the observations we have made so far. Some of those windows sit at masses that would be incredibly useful for explaining other mysteries. Take supermassive black holes, the ones sitting at the centers of galaxies, weighing millions or billions of times the mass of the Sun. We have found some of these monsters at redshifts corresponding to less than 1 billion years after the Big Bang. The James Webb Space Telescope keeps finding more, and every time we find one, the timeline gets tighter. Because growing a billion solar mass black hole from a stellar seed in less than 1 billion years is hard. You need the black hole to feed constantly, at the maximum possible rate, without pause, for hundreds of millions of years. And even then, the math barely works. But if the seed was not a stellar mass black hole, if it was a primordial black hole that formed with a mass of 10,000 or 100,000 solar masses right out of the gate, the timeline relaxes. You still need rapid growth, but you are starting from a much larger base. The gap between what we observe and what the standard models predict gets smaller. Primordial black holes could be the missing piece. Not the whole answer, maybe, but part of it. A head start. a way for the universe to build its largest structures faster than the standard story allows. Hawking did not frame his 1971 paper in those terms. He was not trying to solve the supermassive black hole problem, because in 1971 we did not know supermassive black holes existed. He was working through the logical consequences of general relativity applied to the early universe, and he stumbled onto a result that said black holes could form from density fluctuations. It was a theoretical exercise, a curiosity. He noted that if such objects existed, they might have interesting properties, and then he moved on to other work. It took decades for the rest of the field to catch up, to realize that primordial black holes were not just a footnote in cosmology, that they might be connected to dark matter, to the formation of galaxies, to the existence of supermassive black holes in the early universe, that they might be one of the few ideas we have that can explain multiple observations at once without requiring entirely new physics. The theory is still speculative. No one has found a primordial black hole. No one has directly confirmed that they exist. But the absence of evidence is not evidence of absence, and the gaps in our understanding keep pointing back to the same possibility. Something happened in the early universe that we have not accounted for. Something that built structures faster than they should have been built. Something that left behind a population of dark, invisible objects with masses spanning a range that stellar processes cannot explain. Hawking's whisper, that quiet suggestion from 1971, has gotten louder. Not because the theory has changed, the basic idea is the same as it was 50 years ago, but because the observations have changed. The universe we can see now, with telescopes like JWST, is not behaving the way the standard models predicted. Galaxies are bigger, black holes are heavier, structures are older, and every new observation opens the door a little wider for primordial black holes to step through. If they are real, they would be fossils, relics from a time when the universe was so young and so strange that the rules we rely on today had not yet settled into place. Gravity was the only force that mattered. Density fluctuations were the only seeds. And in that brief chaotic window, before stars, before atoms, before anything stable, the universe stamped out its first black holes and sent them forward through time. We are still looking for them. Still searching the data for the faint gravitational ripples, or the gamma-ray flashes, or the micro-lensing events that would confirm they are out there. The searches have not turned up a smoking gun yet, but they have not ruled them out either. And as long as the possibility remains open, as long as the observations keep pointing towards something missing in the early universe, primordial black holes will stay on the table. Because if Hawking was right, if black holes could form without stars, then the universe did not wait for anything. It did not need stars to build its first anchors. It did not need billions of years to grow its first monsters. It had gravity, it had density, and it had time. And from those three ingredients, in the space of less than a second, it built the seeds that everything else would grow around. If Hawking gave us the theory, the early universe gave us the raw material. Not stars, not gas clouds, not anything you could call matter in the ordinary sense. What the early universe gave us was noise, density noise. Tiny wrinkles in the fabric of space-time itself, stamped into existence before the universe had finished its first breath. And those wrinkles, those microscopic fluctuations in how tightly packed the primordial plasma was from one point to the next, turned out to be the seeds of everything. Every galaxy cluster you can point a telescope at, every black hole, every star, every atom in your body, all of it traces back to those first random ripples in density that formed when the universe was still too young to have a meaningful size. The wrinkles came from inflation. That word gets thrown around a lot in cosmology. usually without much explanation. So let's be precise about what it means. Inflation is the name we give to a period of absurdly rapid expansion that is thought to have occurred in the first tiny fraction of a second after the Big Bang. We are talking about something like 10 to the power of negative 33 seconds after the initial moment. A span of time so short that there is no physical process you can compare it to, no clock that ticks that fast, no event in your life or anyone's life that occurs on that time scale. During inflation, space itself expanded faster than light. That is not a violation of relativity, by the way. Nothing was moving through space faster than light. Space was expanding, and everything in it was being carried along for the ride. In less time than it takes light to cross the width of a proton, the entire observable universe inflated from a region smaller than a subatomic particle to something roughly the size of a grapefruit. Then inflation ended, the expansion slowed to a more reasonable pace, and the universe continued growing at the rate we observe today. Why did inflation happen? Nobody knows. The leading theory involves a hypothetical field called the inflaton field, which is thought to have driven the expansion through some kind of temporary high-energy state before decaying into ordinary matter and radiation. The details are speculative. The math works, the predictions match observations, but the underlying mechanism is still a black box. What matters for this story is not why inflation happened, but what it left behind. Inflation stretched the universe smooth on the largest scales. If you look at the cosmic microwave background, the faint glow of radiation left over from 380,000 years after the Big Bang, it is remarkably uniform. The temperature varies by only about 1 part in 100,000 from one patch of sky to another. That uniformity is a direct consequence of inflation. Any large-scale lumpiness that existed before inflation would have been stretched flat, smoothed out, erased. But inflation did not erase everything. At very small scales, quantum fluctuations in the inflaton field itself created tiny random variations in energy density. These were not classical fluctuations, not ripples in a fluid or vibrations in a solid. They were quantum mechanical in origin, emerging from the fundamental uncertainty that governs the behavior of fields at subatomic scales. During the inflationary period, those quantum fluctuations were stretched along with everything else. What started as microscopic blips in the energy density of the inflaton field got blown up to macroscopic, even cosmic scales. When inflation ended and the inflaton field decayed into ordinary matter and radiation, those stretched quantum fluctuations became density fluctuations in the primordial plasma. Some regions ended up slightly denser than average. Others ended up slightly less dense. The difference was tiny, just a fraction of a percent, but it was there. And once gravity got involved, tiny differences started to matter. The term cosmologists use for these regions is overdensities and underdensities. An overdense region is a patch of space where the density of matter is higher than the surrounding average. An underdense region is the opposite. In the early universe, these variations were everywhere, scattered randomly across space like static on a television screen. Most of them were so small that they had no immediate effect. The universe was still dominated by radiation pressure, a force that resists compression and tries to smooth things out. But gravity does not care about pressure. Gravity pulls, and in regions where the density was high enough, gravity started winning. Here is where the math gets important, so bear with me. There is a critical threshold, a specific density contrast, above which gravity will overwhelm all the forces trying to resist collapse. That threshold is usually expressed as a ratio. If you take the density of a particular region and compare it to the average density of the universe at that time, the ratio needs to be about 1.1 or higher. That means the region has to be at least 10% denser than its surroundings. 10% does not sound like much, but in the early universe where everything was packed absurdly tight, a 10% overdensity represented a staggering concentration of energy in a very small volume. Most density fluctuations did not meet that threshold. They were too weak. Gravity pulled on them, but radiation pressure and the expansion of the universe pushed back harder. The fluctuations stayed small, grew slowly, and eventually became the seeds of galaxies and galaxy clusters billions of years later. But a few regions, the rare sharp peaks in the density distribution, crossed the threshold. In those patches of space, gravity locked on and would not let go. What happens next depends on timing. If the overdensity formed early enough, during the first fraction of a second after the Big Bang, the collapse could be immediate. The region would contract faster than the surrounding universe could expand, pulling more matter inward, compressing itself under its own gravity until it crossed the point of no return. The event horizon forms. Space-time warps so severely that nothing inside can ever escape. You have a black hole, not from a star, not from any kind of astrophysical process we can observe today, just from gravity acting on a density fluctuation that got lucky or unlucky, depending on your perspective. The mass of the resulting black hole would depend entirely on how much matter was contained in the overdense region when it collapsed. A small fluctuation, one that only slightly exceeded the density threshold, might collapse into a black hole weighing no more than a large asteroid. A larger fluctuation could produce a black hole with the mass of a planet, a star, even thousands of stars. There is no inherent limit. The only constraint is how lumpy the early universe actually was, and that depends on the details of inflation, which we still do not fully understand. This is the origin story for primordial black holes. Not all density fluctuations would collapse, most would not, but the ones that did, the rare peaks that crossed the critical density threshold in the first moments after inflation ended, would produce black holes immediately, and those black holes, once formed, would be stable. They would not evaporate, at least not on any time scale that matters, unless they were extraordinarily small. A primordial black hole with a mass greater than about 10 to the power of 12 kilograms, roughly the mass of a small mountain, would still be around today. Anything heavier than that, and you are looking at an object that could survive for trillions of years, far longer than the current age of the universe. So the universe, in its infancy, had the raw ingredients to make black holes without stars. It had density fluctuations, it had gravity. It had an environment where pressure and expansion had not yet smoothed everything out. The question is not whether primordial black holes could form. The physics says they could. The question is whether they did form, and if so, how many of them there are. That question matters because density fluctuations were not just the seeds of black holes, they were the seeds of everything. The same overdensities that could collapse into primordial black holes are also the starting point for structure formation in the universe. The galaxies we see today, the clusters of galaxies, the vast cosmic web of filaments and voids that stretches across billions of light years, all of it grew from those initial density fluctuations. Gravity pulled matter toward the overdense regions, gas clouds contracted, stars formed. Galaxies assembled. Over billions of years, the tiny variations in density that inflation left behind grew into the massive structures we observe. The difference between a region that became a galaxy and a region that became a primordial black hole comes down to timing and scale. Galaxies took time to build. Gas had to cool, collapse, fragment into stars. The process played out over hundreds of millions of years. Primordial black holes, if they formed, did so in less than a second. They were the fast track, the shortcut. Regions where the density was so high and the collapse so immediate that nothing else had time to happen. Gravity won before anything else could intervene. There is a beautiful symmetry here. The universe used the same mechanism, the same initial conditions, to build two completely different kinds of objects. On one hand, you have the slow, patient assembly of galaxies from gas and dark matter, a process that dominates the history of the universe and produces the structures we are most familiar with. On the other hand, you have the rapid, violent collapse of overdense regions into black holes, a process that may have happened only in the first instant, but could have left behind a population of objects that shaped everything that came after. Because primordial black holes, if they existed in significant numbers, would not have just sat there. They would have interacted gravitationally with everything around them. They would have pulled in gas. They would have anchored the formation of the first structures. They might have been the seeds that jump-started galaxy formation, providing the gravitational wells that allowed gas clouds to collapse faster than they otherwise would have. This is not just speculation. Simulations of structure formation in the early universe show that if you seed the simulations with a population of primordial black holes, the structures grow faster, galaxies form earlier, the timeline compresses. You get massive galaxies and supermassive black holes at high redshifts, exactly the kind of objects that telescopes like the James Webb Space Telescope have been finding and that the standard models struggle to explain. The connection between primordial black holes and large-scale structure is one of the reasons the theory has gotten more attention in recent years. It is not just about explaining where black holes came from. It is about explaining why the universe looks the way it does, why galaxies formed as quickly as they did, why supermassive black holes were already in place less than 1 billion years after the Big Bang, why the cosmic web has the structure it has. Density fluctuations are the thread that ties all of this together. They are the starting point. The initial condition, the moment where quantum noise in an inflaton field turned into macroscopic variations in the density of the universe, and those variations became the template for everything that followed. Some of those fluctuations grew slowly into galaxies, others collapsed instantly into black holes, and the black holes in turn may have helped shape the galaxies. Let's talk specifics. The cosmic microwave background gives us a detailed map of the density fluctuations as they existed 380,000 years after the Big Bang. By that time, the fluctuations had grown slightly under the influence of gravity, but they were still small. The densest regions were only about 1 part in 100,000 denser than the average. That is nowhere near the 10% threshold needed for a primordial black hole to form. So how do you get from 1 part in 100,000 to 10%? The answer is that by the time we see the cosmic microwave background, the window for primordial black hole formation has already closed. The density fluctuations visible in the CMB are the ones that did not collapse. They are the survivors. The fluctuations that did cross the collapse threshold would have done so much earlier, during the first second after the Big Bang, when the universe was far denser and the contrast between overdense and underdense regions could be much sharper. The fluctuations we see in the CMB are the ones that were too weak to collapse on their own. They needed time, they needed gravity to slowly amplify them over hundreds of millions of years. By the time the first stars ignited, those fluctuations had grown into the density peaks that became the first galaxies. But the primordial black holes, if they formed, would already have been there waiting. Silent anchors embedded in the fabric of the universe, pulling on the surrounding gas, shaping the flow of matter, influencing where and how the first structures assembled. One of the challenges in testing this idea is that we cannot directly observe the density fluctuations in the first second after the Big Bang. The universe was opaque. Light could not travel freely. All we have are models and simulations, and those depend on assumptions about what inflation did and how the inflaton field behaved. Different models of inflation produce different predictions for the amplitude and distribution of density fluctuations. Some models predict a smooth distribution with very few high-density peaks. Others predict a rougher distribution with more sharp peaks, which would increase the likelihood of primordial black hole formation. The observations we do have, the ones from the CMB and from large-scale structure surveys, tell us that the universe was relatively smooth. Most of the density fluctuations were small, but relatively smooth still leaves room for rare high-density peaks, and rare does not mean non-existent. If even a tiny fraction of the early universe's volume contained overdensities that exceeded the collapse threshold, you could still end up with a significant population of primordial black holes scattered throughout the cosmos. How significant? That depends on the model. Some estimates suggest primordial black holes could make up a substantial fraction of the dark matter in the universe. Others suggest they are rare, contributing only a tiny percentage of the total mass budget. The truth is, we do not know. The constraints from observations are loose enough that a wide range of scenarios are still on the table. What we do know is that density fluctuations were not optional. They were baked into the universe by inflation, and once you have density fluctuations, you have the possibility of collapse. Gravity does not care about your theoretical preferences. It does not care whether you think primordial black holes are likely or unlikely. It cares about density, and if the density exceeded the threshold, collapse would happen. The physics is straightforward. The question is purely empirical. Did the early universe produce enough high-density peaks to make a difference? There is another angle to this that does not get discussed much but matters enormously. Density fluctuations were not just the seeds of black holes and galaxies. They were also the seeds of the cosmic web itself, the large-scale structure of the universe. The way galaxies are distributed in vast filaments with enormous voids in between is a direct consequence of how gravity acted on the initial density fluctuations. Over-dense regions pulled matter toward them, creating filaments and clusters. Under-dense regions lost matter, becoming voids. If primordial black holes formed in the densest peaks, they would have been embedded in the nodes of the cosmic web from the very beginning. They would have sat at the intersections of filaments, in the centers of the densest regions, exactly where you would expect to find the seeds of galaxy clusters. And as matter flowed along the filaments and accumulated in those nodes, the primordial black holes would have grown. Not dramatically, not at the rate we see in active quasars today, but steadily, slowly building mass over billions of years as gas and dark matter drifted into their gravitational wells. This is one way to bridge the gap between primordial black holes and the supermassive black holes we see today. You do not need every supermassive black hole to have started as a primordial seed, but if even a small fraction of them did, it would explain how black holes weighing millions or billions of solar masses could exist so early in the universe's history. You start with a heavy seed, a primordial black hole with the mass of thousands or tens of thousands of suns, and you give it a few 100 million years to feed. The math gets a lot easier. The timeline stops looking impossible. The connection between gravitational seeds and large-scale structure is not just theoretical. It is built into the way structure formation works. Gravity amplifies density contrasts. Over-dense regions get denser. Under-dense regions get emptier. The process feeds on itself, creating a runaway effect where the rich get richer and the poor get poorer. In a universe with primordial black holes, those black holes would be sitting in the richest regions from the start. They would be the anchors around which the first galaxies formed, the gravitational wells that pulled in the gas that ignited the first stars. And the first stars, when they died, would have added to the black hole population. Stellar mass black holes forming from supernovae, falling toward the centers of the gravitational wells, merging with the primordial seeds, building up the mass over time. You end up with a hybrid model where both primordial black holes and stellar black holes contribute to the final population. The primordial seeds provide the head start. The stellar remnants provide the steady growth. Together, they produce the supermassive monsters we see at the centers of galaxies today. None of this is proven, but the logic is sound, the physics is consistent, and the observations, the ones that keep showing us black holes that are too big and too old to fit comfortably into the standard story, keep pointing back toward the possibility that something happened in the early universe that we have not fully accounted for. That the density fluctuations inflation left behind were not just the seeds of galaxies, they were the seeds of black holes. And those black holes, formed in the first instant, may have been the universe's first permanent structures, the first anchors, the first building blocks around which everything else assembled. The universe did not wait for stars to start building. It used what it had: gravity, density, and a brief chaotic moment where the rules had not yet settled. From that moment, from those gravitational seeds, it built the scaffolding for everything that followed. Some of those seeds grew into galaxies, others collapsed into black holes, and the black holes, silent and invisible, may have been guiding the process from the very beginning, shaping the flow of matter, anchoring the structures, pulling the universe into the form we see today. If that is true, then the monsters we are about to meet, the supermassive black holes lurking at the dawn of time, are not accidents, they are not anomalies. They are the descendants of those first gravitational seeds, the children of inflation, and their existence tells us that the universe was never as simple or as slow as we thought. If the early universe spent its first second stamping out black holes from primordial density fluctuations, then those black holes should have been sitting in the cosmos, quiet and invisible, waiting for the rest of creation to catch up. That is what the theory predicts. Small black holes, large black holes, scattered across space like seeds in soil, embedded in the fabric of the expanding universe long before the first star ever ignited. They would not do much at first, just sit there, exerting gravity, pulling gently on the gas and dark matter drifting past. Patient, stable, invisible to any instrument we could point at them, because black holes do not glow unless they are feeding, and in the early universe there was not much to feed on yet. Just thin clouds of hydrogen and helium, cooling as the cosmos expanded, waiting for gravity to pull them into something interesting. Then the first stars lit up. Population 3 stars, massive blue giants burning hydrogen at a ferocious rate, living fast and dying young. When the biggest ones exhausted their fuel and went supernova, their cores collapsed into stellar mass black holes, a few dozen solar masses each, maybe 100 at the extreme upper end. These are the black holes we understand, the ones we have seen forming in the modern universe. The ones that fit neatly into the standard story of how massive stars die. And then we pointed telescopes at the early universe and found black holes that should not exist, not small ones, not the kind you get from a single dead star. Monsters. Supermassive black holes weighing hundreds of millions of solar masses, some pushing into the billions, sitting at the centers of galaxies that formed less than 1 billion years after the Big Bang. In some cases, less than 700 million years. Quasars blazing so brightly that we can see them across more than 13 billion light-years of space, their light stretched and redshifted by the expansion of the universe, but still powerful enough to register in our instruments as clear, undeniable signals. These objects are real. They are out there, and every single one of them is a problem. The problem is time, or more precisely, the lack of it. A stellar mass black hole that forms from a supernova starts with a mass of maybe 10 to 100 times the mass of the Sun. To grow from that starting point to a billion solar masses, it needs to feed, constantly, at the absolute maximum rate that physics allows. That rate is called the Eddington limit, and it is set by a balance between gravity pulling matter inward and radiation pressure pushing it outward. When a black hole feeds, the infalling gas heats up to millions of degrees and emits intense radiation. That radiation pushes back on the surrounding gas, creating a kind of traffic jam at the event horizon. Only so much matter can fall in per unit of time before the radiation pressure becomes strong enough to blow the rest away. The Eddington limit is not a suggestion. It is a hard physical constraint. A black hole feeding at the Eddington limit will roughly double its mass every 50 million years or so. That sounds fast. It is fast. But run the numbers and you hit a wall. Start with 100 solar mass black hole. Give it 50 million years and it grows to 200 solar masses. Another 50 million years and you are at 400. Another 50 million and you are at 800. You can see where this is going. To reach a billion solar masses, starting from a stellar seed, you need at least 20 doubling periods. 20 times 50 million years is a billion years, and that is assuming the black hole never stops feeding. Not for a moment, not when its host galaxy runs out of gas. Not when radiation pressure blows the surrounding material away. Not when a supernova in a nearby star disrupts the accretion disk. Never. Perfect feeding, perfect conditions, perfect efficiency for a billion years straight. The universe is not perfect. Real black holes do not feed continuously. They go through active phases and quiet phases. They run out of nearby gas. They get kicked by gravitational interactions with other black holes or passing stars. The growth is episodic, not smooth. Factor that in, and the timeline stretches even further. You might need 2 billion years or more to grow a supermassive black hole from a stellar seed under realistic conditions. That would be fine if we were finding these supermassive black holes in galaxies that are 10 or 11 billion years old. We are not. We are finding them in galaxies that are less than a billion years old. Some of them existed when the universe itself was only 690 million years old. At that point in cosmic history, the first stars had only been burning for a few 100 million years at most. There simply has not been enough time to grow a billion solar mass black hole from a stellar seed, even under the most optimistic assumptions. The numbers do not work. They do not come close. One of the earliest and most dramatic examples came from observations of a quasar detected at a redshift corresponding to about 690 million years after the Big Bang. The quasar, which is just the bright accretion disk surrounding a supermassive black hole as it feeds, was shining with the light of trillions of stars. The black hole powering it was estimated to weigh about 800 million times the mass of our Sun. That is not a typo. 800 million solar masses, less than 700 million years after the Big Bang. To put that in perspective, our own Milky Way galaxy has a supermassive black hole at its center called Sagittarius A star. It weighs about 4 million solar masses. The black hole in this early quasar was 200 times heavier, and it existed when the universe was less than 5% of its current age. The Milky Way has had more than 13 billion years to build its central black hole. This thing did it in less than a billion. The discovery made headlines. Not because quasars were new, we have known about quasars since the 1960s, but because finding one this massive this early violated every reasonable model of black hole growth. Astronomers started calling it the impossibly early quasar problem, though that name undersells how serious the issue is. This is not a minor discrepancy. This is a foundational crack in the standard story of how the universe builds its largest structures. Then the James Webb Space Telescope turned on, and the cracks got wider. Webb was designed to see further back in time than any telescope before it. Its massive mirror and infrared sensitivity allow it to detect light from the earliest galaxies, the ones that formed in the first few 100 million years after the Big Bang. And almost immediately, it started finding supermassive black holes where they should not be. Not just one or two outliers, but a whole population of them. Black holes weighing tens of millions or hundreds of millions of solar masses, sitting in galaxies so young that the standard models predicted they should barely have had time to form stars, let alone grow supermassive black holes. One of the most striking discoveries came from a galaxy called U8Z1. The black hole at its center was detected at a distance of about 13.2 billion light-years, meaning we are seeing it as it existed roughly 470 million years after the Big Bang. The black hole weighs about 10 times as much as the Milky Way's central black hole, putting it at around 40 million solar masses. That might not sound as dramatic as the 800 million solar mass monster from the earlier quasar, but UAGDA1 is even younger. It existed when the universe was barely 3.5% of its current age. There is no conventional pathway to grow a 40 million solar mass black hole in that amount of time, starting from a stellar seed. A researcher quoted in coverage of the discovery said what was surprising was not just that the black hole was there, but that it seemed to be fully formed, not a young black hole still growing into maturity. A fully developed supermassive black hole sitting at the center of a galaxy, doing what supermassive black holes do, at an age when the universe should not have had time to build such a thing. Surveys conducted with both ground-based telescopes and space observatories have now catalogued dozens of these early supermassive black holes. One survey identified 83 quasars powered by supermassive black holes in the early universe, all of them existing when the universe was less than 10% of its current age. That is not a handful of outliers, that is a population, a common feature of the early cosmos. Supermassive black holes were not rare anomalies in the first billion years. They were everywhere. That fact alone should make you pause. Because if supermassive black holes were common in the early universe, then whatever process built them was not some exotic edge case. It was part of the standard operating procedure. The universe was mass-producing supermassive black holes in its infancy, and we do not have a good explanation for how it did that. The obvious question is whether there is some way to make the standard story work. Maybe black holes in the early universe fed faster than the Eddington limit. Maybe the conditions were different. Maybe radiation pressure was less effective at blocking accretion, allowing matter to pile onto black holes at super Eddington rates. Some models have explored this possibility. The idea is that in the dense, gas-rich environments of the early universe, black holes could have been buried in thick clouds of gas that absorbed the outgoing radiation before it could push new material away. If the radiation could not escape efficiently, it could not create the pressure barrier that normally limits accretion. The black hole could gorge itself, growing much faster than the Eddington limit would normally allow. That scenario has problems. For one thing, super Eddington accretion is messy. It generates enormous amounts of heat and radiation. And even if the radiation gets trapped temporarily, it eventually has to go somewhere. Models suggest that super Eddington growth can only be sustained for short bursts before the system blows itself apart. You might get a factor of a few in extra growth, but not the orders of magnitude needed to explain an 800 million solar mass black hole at 690 million years. Another idea is that black holes in the early universe grew primarily through mergers. If stellar mass black holes formed in dense clusters and then collided and merged with each other repeatedly, you could build up a larger black hole relatively quickly. Each merger adds mass, and if the mergers happen in rapid succession, you could climb the mass ladder faster than you could through accretion alone. That idea also has limits. Mergers take time. Two black holes do not collide the moment they form. They have to drift toward each other, lose energy through gravitational radiation, and spiral inward. Even in a dense star cluster, the timescale for black hole mergers is measured in tens or hundreds of millions of years, and each merger only adds a modest amount of mass. You would need dozens or hundreds of mergers to build a supermassive black hole, and the early universe simply does not provide enough time for that many events to occur in sequence. So neither super-Eddington accretion nor runaway mergers can fully explain what we are seeing. The timeline is just too tight. The black holes are too massive, too early. And that brings us back to the possibility we started with. Maybe the seeds were not small. Maybe some black holes did not start as stellar remnants at all. If primordial black holes formed in the first second after the Big Bang, their masses were not constrained by stellar physics. A stellar black hole forms from a collapsing star, so its mass is limited by the mass of the star. The biggest stars we know about weigh a few hundred solar masses at most, and most of that mass gets blown off in the supernova. The black hole that is left behind is only a fraction of the original star's mass, but a primordial black hole forms from a density fluctuation. It can have whatever mass the density fluctuation contained. That could be a few solar masses, or a few thousand, or a few 100,000 or more. There is no inherent upper limit. Start with a primordial black hole weighing 10,000 solar masses, and the math changes completely. Give it 500 million years to feed at the Eddington limit, and it grows to several million solar masses. Push the feeding rate a bit higher, or extend the timeline slightly, and you can reach tens of millions, or even hundreds of millions of solar masses. Suddenly the observations do not look impossible anymore. They look plausible. This is the primordial black hole as seed hypothesis. The idea is that at least some of the supermassive black holes we see in the early universe did not grow from stellar remnants. They grew from primordial seeds, black holes that formed in the immediate aftermath of the Big Bang and sat waiting in the dense cores of the first dark matter halos. When gas began collapsing into those halos to form the first galaxies, the primordial black holes were already there, acting as gravitational anchors. The gas piled in, the black holes fed, and within a few 100 million years, you had supermassive black holes weighing millions or billions of solar masses. The hypothesis is compelling because it solves the timeline problem without requiring exotic physics. You do not need super-Eddington accretion. You do not need hundreds of rapid-fire mergers. You just need a head start, a heavier seed, and primordial black holes, if they exist, provide exactly that. There is observational support for the idea, though it is indirect. A study using data from NASA's Spitzer Space Telescope and other infrared observatories found that black holes in the early universe, between 400 million and 800 million years after the Big Bang, were responsible for at least 20% of the cosmic infrared background. That is a measure of all the infrared light filling the universe, and 20% is a significant chunk. The study's lead author, Alexander Kashlinsky from NASA Goddard, noted that the black holes appeared to be well established by that point in time, implying they had already been growing for a while. If they had already been growing, they must have started earlier. And if they started earlier, they needed seeds that were already in place. Another study, this one focused on X-ray observations from the Chandra Space Telescope, looked at how early black holes grew over time. The results suggested that the growth was episodic, with black holes going through active feeding phases interspersed with quieter periods. That is consistent with what we expect from real accretion processes. But even accounting for the episodic nature of the growth, the models still required black holes weighing about 1 billion solar masses to exist by roughly 12.8 billion years ago, which is about 950 million years after the Big Bang. To get there, the seeds had to start heavy. Rosa Valianti, one of the researchers involved in the study, noted that in their model, only about a third of black holes were actively consuming material and growing 13 billion years ago. That implies a large population of black holes was already present, many of them sitting dormant, waiting for gas to drift within reach. The picture that emerges from these observations is one where supermassive black holes were not rare flukes in the early universe. They were common. They were widespread, and they were massive enough, early enough, that the standard stellar collapse pathway cannot account for them. Something else had to seed their growth, and primordial black holes are one of the few ideas that fits. But primordial black holes are still hypothetical. No one has ever directly detected one. No one has found a smoking gun that proves they exist. The evidence is circumstantial, suggestive. The observations point toward a missing population of heavy seeds, and primordial black holes fit the bill. But that does not mean they are the only explanation. Other ideas are still on the table. Direct collapse black holes, for instance, where a massive gas cloud in the early universe skips the star formation step entirely and collapses straight into a black hole weighing tens of thousands of solar masses. That could also provide the heavy seeds needed to explain early supermassive black holes. The difference is that direct collapse requires very specific conditions. The gas has to stay hot enough that it cannot fragment into stars. That means no cooling, no molecular hydrogen, no metals. Those conditions might have existed in a few rare pockets of the early universe, but it is hard to see how they could have been common enough to produce the large population of supermassive black holes we observe. Primordial black holes, on the other hand, form from density fluctuations. If the early universe was lumpy enough, you get primordial black holes automatically. No special conditions required. That is one reason the primordial seed hypothesis has gained traction. It does not require the universe to be finely tuned. It just requires the universe to be lumpy, and we already know it was lumpy. The cosmic microwave background tells us that. The question is whether the lumps were sharp enough, dense enough, to produce a significant population of primordial black holes in the mass range that would matter for seeding supermassive black holes. The answer to that question depends on the details of inflation, and those details are still being worked out. What we can say with confidence is that the supermassive black holes in the early universe are not behaving the way the standard models predicted. They are too massive. They are too common, they formed too quickly, and the gap between what the models predict and what we observe is not small. It is enormous. It is the kind of gap that suggests something fundamental is missing from our understanding. The implications go beyond black holes. If primordial black holes seeded the formation of supermassive black holes, they also seeded the formation of galaxies, because galaxies and their central black holes grow together. The mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's bulge, the dense central region where most of the stars are concentrated. That correlation holds across the entire range of observed galaxies, from small ones to giant ellipticals. The relationship is so tight that astronomers treat it as a fundamental law of galaxy formation. Somehow, the black hole and the galaxy know about each other. They grow in lockstep. If the black hole starts as a primordial seed, then the galaxy builds itself around that seed. The black hole is not a byproduct of galaxy formation. It is the starting point, the anchor, the gravitational well that pulls in the gas and dark matter that eventually become the galaxy, that flips the usual story on its head. We are used to thinking of galaxies as the main event and black holes as a side effect. But if primordial black holes seeded galaxy formation, then black holes came first. Galaxies grew around them. The monsters of the dawn were not anomalies, they were architects. That is a deeply strange idea. It suggests that the universe's largest structures, the galaxies that fill the cosmic web, owe their existence to objects that formed in the first second after the Big Bang. Objects that were not stars, not gas clouds, not anything we can see, just gravity. Pure concentrated gravity sitting in the dark, waiting for the universe to deliver the raw materials needed to build something visible. And if that is true, then the black holes we are finding in the early universe, the ones that keep surprising us with their size and their age, are not telling us that the models are wrong. They are telling us that we have been looking at the story backward. We thought galaxies made black holes. Maybe black holes made galaxies. We thought stars had to come first. Maybe gravity came first. We thought the universe needed billions of years to build its monsters. Maybe the monsters were there from the beginning, woven into the fabric of creation before the first light ever dawned. The universe is 13.8 billion years old. We have spent most of that time assuming we understood the order in which things were built. Stars, then black holes, gas clouds, then galaxies. Simple structures first, complex ones later. That story worked for a long time. It explained what we could see with our telescopes. It fit the observations we had, and then we built better telescopes, looked deeper into the past, and found a universe that did not follow the script. A universe that had already built supermassive black holes when it was barely old enough to have built stars. A universe that started with monsters, not because it broke the rules, but because the rules we wrote were incomplete. Primordial black holes are not the only possible answer, but they are the answer that keeps fitting the observations, the one that turns the impossibly early into the merely unexpected, the one that says the universe did not need to wait. It had seeds, it had gravity, and it had time, just not the amount of time we thought it needed. From those ingredients, in a span of a few 100 million years, it built the largest black holes ever observed, sitting at the centers of the earliest galaxies, shaping the flow of matter and light across billions of light years. And those black holes, whether they started as primordial seeds or something else entirely, are still out there, still growing, still feeding. Some of them have survived for more than 13 billion years, outlasting stars, outlasting galaxies, outlasting entire epochs of cosmic history. They are the ultimate survivors, and understanding how they survived, how they grew, and what they tell us about the universe's first moments is the next piece of the puzzle. The universe has a filing system, and it is organized by mass. Stars sort themselves neatly into categories. Red dwarfs at the bottom, barely massive enough to fuse hydrogen. Giants in the middle, hypergiants at the top, burning so hot and so fast that they exhaust themselves in a few million years. Black holes formed from those stars inherit the same sorting system. A few solar masses on the low end, maybe 100 at the extreme upper limit, clean boundaries, predictable outcomes, the kind of order that makes astrophysics textbooks possible. Primordial black holes do not respect that filing system. They were not constrained by the mass of a collapsing star because they did not form from stars. They formed from density fluctuations in the early universe, and those fluctuations came in every size. The smallest ones, the ones that formed from the tiniest quantum wrinkles in the fabric of space-time during inflation, could have masses near the Planck scale. That is about 10 to the power of -5 grams, roughly the mass of a flea egg, compressed into a region far smaller than a proton. A black hole so small that calling it microscopic would be an overstatement. At the other end of the spectrum, the largest primordial black holes could have formed from density fluctuations that encompassed enormous volumes of the early universe. Some models allow for primordial black holes weighing hundreds of solar masses. Others push the upper limit to thousands or even hundreds of thousands of solar masses. A few highly speculative scenarios suggest primordial black holes could have formed with masses reaching into the millions of solar masses, rivaling the supermassive black holes we see at the centers of galaxies today. The range is not just broad, it is absurd, spanning more than 50 orders of magnitude from the Planck mass to a million solar masses. No other object in the universe occupies that kind of mass spectrum. That range matters because the mass of a black hole determines everything about its behavior, how it interacts with matter, how long it survives, whether we have any hope of detecting it. A primordial black hole at the low end of the mass spectrum would have evaporated billions of years ago, its mass radiated away as a faint quantum hiss. A primordial black hole at the high end would still be sitting in the cosmos today, effectively immortal, slowly accreting matter and growing larger with every passing eon. Between those extremes, you have a zoo of possibilities, black holes that evaporated in the first seconds after the Big Bang. Black holes that are evaporating right now, in the final moments of their existence. Black holes that will outlive the stars, and black holes so massive that they will outlive the universe itself in any meaningful sense. Let's start at the bottom and work our way up, because the smallest primordial black holes are where the story gets weird. A primordial black hole with a mass near the Planck scale, around 10 to the power of -5 grams, would have an event horizon smaller than the smallest distance we can meaningfully measure. The Planck length, about 10 to the power of -33 centimeters, is the scale at which quantum mechanics and general relativity stop playing nicely together. Below that scale, space-time itself becomes a fuzzy, probabilistic thing that our equations cannot describe. A black hole with an event horizon at or below the Planck length is not just small, it is smaller than the concept of size has any clear meaning, and it would not last. Black holes, it turns out, are not entirely black. Stephen Hawking showed in the 1970s that black holes emit radiation due to quantum effects near the event horizon. The process is subtle. Virtual particle pairs, the fleeting fluctuations that pop in and out of existence throughout empty space, occasionally appear right at the edge of a black hole's event horizon. Normally, the particle and antiparticle annihilate each other almost immediately. But near a black hole, one member of the pair can fall across the event horizon while the other escapes. To an outside observer, it looks like the black hole is radiating particles. The energy for those particles has to come from somewhere, and the only source is the black hole's mass. So the black hole loses mass, slowly at first, then faster as it gets smaller. The rate of evaporation depends on the black hole's size. Larger black holes radiate more slowly, smaller black holes radiate faster. The relationship is steep. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate. That is so absurdly long that the number stops having meaning. The universe is only about 10 to the power of 10 years old. Even if you waited a trillion times longer than the current age of the universe, a solar mass black hole would barely have begun to shrink. But a primordial black hole near the Planck mass would evaporate almost instantly. The time scale for evaporation scales with the cube of the mass, so drop the mass by a factor of 1 billion and the evaporation time drops by a factor of 1 billion cubed. A Planck mass black hole would radiate away its entire mass in something like 10 to the power of -40 seconds. That is not a blink. That is not even a fraction of a blink. It is a span of time so short that no physical process we know of operates on that scale. The black hole would form and vanish in less time than it takes light to cross the diameter of its own event horizon. So the tiniest primordial black holes, if they formed, are long gone. They evaporated in the first instant after the Big Bang, their mass converted into a burst of radiation that has since been stretched and diluted by the expansion of the universe into undetectability. They left no trace, no fossils, no remnants, just a brief flicker of energy that dissipated before the universe was old enough to notice. Scale up slightly, and things get more interesting. A primordial black hole with a mass around 10 to the power of 12 kilograms, roughly the mass of a small mountain, would have an evaporation timescale comparable to the current age of the universe. That is about 14 billion years. If such a black hole formed in the first second after the Big Bang, it would be finishing its evaporation right now. Not yesterday, not a million years ago, now, today. In the time it takes you to watch this, somewhere in the universe, a primordial black hole that has been quietly radiating for 13.8 billion years might be entering its final moments. Those final moments would be dramatic. As the black hole's mass drops, its temperature rises. Hawking radiation is thermal, meaning it has a temperature associated with it, and the temperature is inversely proportional to the mass. A black hole with the mass of a mountain would have a temperature of about 1 billion degrees Kelvin, hot enough to emit gamma rays. As it loses mass and heats up further, the radiation gets more intense. The black hole glows brighter and brighter, emitting higher and higher energy photons, until in the last fraction of a second, it releases a final burst of gamma rays and disappears. That burst, if we could detect it, would be a smoking gun, proof that primordial black holes exist, or existed. Astronomers have looked for these gamma ray flashes. Satellites, like the Fermat Gamma Ray Space Telescope, have surveyed the sky for unexplained bursts of high-energy radiation. So far, nothing, no clear signal that matches the expected profile of an evaporating primordial black hole. That does not mean they are not out there. It just means that if they exist, they are either very rare or the ones small enough to evaporate have already done so in regions of space we were not watching at the right time. There is a threshold mass that matters enormously for this story. It sits around 4 times 10 to the power of 14 grams, give or take. That is roughly 10 to the power of 11 kilograms, or about 100 billion kilograms if you want to think of it in human units. Still small by astronomical standards, less than the mass of a small asteroid. But black holes above that mass have evaporation timescales longer than the age of the universe. They would have formed in the first moments after the Big Bang, and they would still be around today, radiating so slowly that their mass loss is negligible over billions of years. They are, for all practical purposes, stable. That threshold is why the mass range around 10 to the power of 14 grams gets so much attention in the literature. Black holes just below that mass are finishing their evaporation now or in the recent past. Black holes just above that mass are survivors. They made it through the entire history of the universe, and they are still here, invisible and undetectable by most of our instruments, but real and persistent and contributing to the overall mass budget of the cosmos. Go larger still, and the evaporation becomes irrelevant. A primordial black hole with a mass of 10 to the power of 15 grams or more would radiate so slowly that even over trillions of years it would lose only a tiny fraction of its mass. These black holes are not on borrowed time. They are permanent fixtures. They will outlive stars. They will outlive galaxies. They will outlive the formation of new stars entirely. In the far future, when the universe has expanded so much that star formation has ceased and the last red dwarfs have burned out, primordial black holes in this mass range will still be sitting in the dark, patient and unchanged, waiting for the occasional stray particle to drift within reach. The mass of a primordial black hole is tied to when and how it formed. The early universe was not a uniform soup. It had structure at every scale, from the largest density fluctuations that would eventually become galaxy clusters down to the tiniest quantum wrinkles in the inflaton field. The mass of a primordial black hole depends on the size of the density fluctuation that collapsed to form it and the horizon scale at the time of collapse. The horizon scale is a concept from cosmology that describes the maximum distance over which regions of space can be causally connected at a given moment. In the first fraction of a second after the Big Bang, the horizon was tiny. A density fluctuation that collapsed into a black hole at that moment could only encompass a small region, so the resulting black hole would have a small mass. As the universe expanded and the horizon grew, larger regions could collapse, producing more massive black holes. By the time the universe was a second old, the horizon had grown large enough that density fluctuations collapsing at that moment could produce black holes weighing a few solar masses or more. That relationship between formation time and mass is why primordial black holes span such an enormous range. The ones that formed earliest are the smallest. The ones that formed latest are the largest. And because the universe went through different phases, each with its own characteristic density and expansion rate, the formation conditions varied. During the radiation-dominated era, which lasted for the first few tens of thousands of years, the universe was hot and dense and expanding rapidly. Density fluctuations had to be sharp and strong to overcome the pressure and collapse. During the matter-dominated era, which began after the cosmic microwave background was released, the universe had cooled enough that pressure was less of a barrier. Density fluctuations could collapse more easily, but by then, the horizon scale was so large that any black holes forming would be much more massive. The result is a mass spectrum, a distribution of primordial black holes across different mass ranges, with the shape of that distribution depending on the details of how lumpy the early universe was at different times. Some models predict a smooth distribution with roughly equal numbers of black holes at every mass. Others predict spikes at specific masses, corresponding to moments when the conditions were especially favorable for black hole formation. Still others predict gaps, mass ranges where almost no primordial black holes formed because the density fluctuations at that scale were too weak. We do not know which model is correct because we do not have direct observations of primordial black holes. What we have are constraints, observations that rule out certain parts of the mass spectrum. If primordial black holes existed in large numbers at a particular mass, they would leave detectable signatures: gravitational lensing, gamma-ray bursts from evaporation, distortions in the cosmic microwave background, perturbations in the orbits of planets or stars. Surveys have looked for all of these effects and in many cases come up empty. That does not mean primordial black holes do not exist. It means they do not exist in large enough numbers at those specific masses to produce signals we can detect with current instruments. But there are gaps in the constraints, windows where a population of primordial black holes could be hiding without violating any observations. One such window sits around 10 to the power of 17 grams, roughly the mass of a small moon. Black holes in that range would be too light to produce strong gravitational lensing on the scales we have surveyed. They would be too heavy to evaporate and produce gamma rays. They would not disrupt planetary orbits unless they passed very close, and the odds of a close pass are low. They could be out there, scattered throughout the galaxy, and we might never notice. Another window sits at much higher masses, around 10 to the power of 1 to 10 to the power of 2 solar masses. Primordial black holes in that range would be heavy enough to contribute significantly to the dark matter budget. They would not radiate. They would not lens light in ways we can easily detect with current surveys. And they would be rare enough, spread out enough, that the odds of one passing close to a star or planet and producing a detectable disturbance are very small. If primordial black holes exist in that mass range, they are essentially invisible. Dark anchors drifting through the galaxy, pulling on the surrounding matter with their gravity, but producing no light, no heat, no radiation that we can detect from a distance. The idea that invisible black holes could be floating through the solar system right now is unsettling. A primordial black hole with a mass of 10 solar masses would have an event horizon about 60 kilometers across. Not large by astronomical standards, smaller than most cities. If one passed through the Earth, it would punch a narrow tunnel through the planet, heating the rock along its path, and exit the other side. The encounter might trigger earthquakes along the tunnel if the trajectory passed through a seismically active region. But if the black hole missed the crust and passed through the mantle or core, the surface might not notice at all. The black hole would slip through like a needle through foam, its gravitational field too localized to disturb anything more than a few kilometers from its path. The odds of such an encounter are low. Space is big. Even if the galaxy is filled with primordial black holes, the volume is so vast and the cross-section of the Earth is so small that a direct hit would be extraordinarily rare. But rare is not the same as impossible. If primordial black holes exist in the numbers some models predict, there could be thousands of them within a few light years of the Sun. Most would be drifting in interstellar space, far from anything solid. But a few might pass through the solar system every few million years, close enough to the planets or the Sun to leave faint gravitational traces. One paper explored the idea of using the orbits of planets to search for primordial black holes. If a heavy primordial black hole passed near a planet, the gravitational tug would slightly alter the planet's orbit. The change would be tiny, a fraction of a percent. But over time, it would accumulate. If we have precise enough measurements of planetary orbits over long enough timescales, we might be able to detect those perturbations and infer the presence of a passing black hole. So far, no such signal has been found, but the searches are still in their infancy. The datasets are improving. And if primordial black holes are out there, this kind of indirect detection might be the only way we ever confirm their existence. The largest primordial black holes, the ones at the extreme upper end of the mass spectrum, blur the line between primordial and supermassive. A primordial black hole weighing 100,000 solar masses or more would be indistinguishable in its properties from a supermassive black hole that formed later through stellar processes or direct collapse. The only difference would be its origin story. If such a black hole formed in the first second after the Big Bang, it would already have been sitting in the universe when the first stars ignited. It would have been one of the anchors around which the first galaxies assembled. It would have fed on the gas collapsing into the early dark matter halos, growing steadily over hundreds of millions of years, and by the time the universe was 1 billion years old, it could have reached millions or even billions of solar masses. This is the connection between primordial black holes and the impossibly early supermassive black holes we talked about in the last chapter. If the seeds were primordial, if they started heavy, the timeline problem goes away. You do not need to explain how a stellar mass black hole grew to 1 billion solar masses in less than 1 billion years. You just need a primordial seed weighing 10,000 or 100,000 solar masses, give it access to a steady supply of gas, and let it grow at a reasonable rate. The math works, the observations fit, And the only assumption you need is that the early universe was lumpy enough to produce a small population of very massive primordial black holes. The implications extend beyond supermassive black holes. If primordial black holes exist across a wide mass range, they could be contributing to multiple observed phenomena. The smallest survivors, the ones just above the evaporation threshold, could be part of the dark matter. The intermediate mass ones, weighing tens or hundreds of solar masses, could be responsible for some of the gravitational wave signals detected by LIGO and other observatories. The largest ones could be the seeds of supermassive black holes, and the ones in the gaps, the mass ranges where we have no strong constraints, could be out there in numbers we have not yet ruled out, quietly shaping the dynamics of galaxies and the flow of matter on scales we have not thought to look at carefully. The challenge is detection. Black holes do not glow, they do not radiate unless they are feeding, and even then, the radiation comes from the surrounding material, not the black hole itself. A primordial black hole drifting through empty space produces no light, no heat, no electromagnetic signal of any kind. The only way we know it is there is through its gravity, and gravity is subtle. A black hole has to pass close to something or accumulate enough mass over time to produce a lensing effect or a measurable perturbation before we can detect it indirectly. That is why the search for primordial black holes has been so difficult. We are looking for objects that are small, dark, and rare, scattered across a volume of space so large that the odds of any one of them passing close enough to a detector to register are vanishingly small. It is like trying to find a handful of invisible needles in a haystack the size of a galaxy. Possible in theory, extraordinarily hard in practice, but the searches continue. New telescopes, new gravitational wave detectors, new techniques for analyzing the subtle distortions in starlight caused by passing massive objects. Each new tool opens a window into a different part of the mass spectrum. Each new observation tightens the constraints or expands the gaps where primordial black holes could still be hiding. And the fact that we have not found them yet does not mean they are not there. It just means they are very good at being invisible. There is a certain elegance to the idea that the universe could be filled with black holes spanning 50 orders of magnitude in mass, all formed in the same brief chaotic moment after the Big Bang, all shaped by the same underlying physics. The smallest ones evaporated almost immediately, their brief existence leaving no mark on the cosmos. The largest ones survived, became the seeds of galaxies, and are still growing today. And in between, across the entire mass range, you have a population of cosmic survivors. Black holes that formed before atoms, before stars, before anything you could call structure, and that have been drifting through the expanding universe ever since, silent witnesses to the entire history of creation. If primordial black holes exist, they are the oldest objects in the universe. Older than the cosmic microwave background, older than the first stars, older than galaxies. They are fossils from the first instant, carrying information about conditions in the early universe that we cannot access any other way. Their masses encode the details of the density fluctuations that formed them. Their distribution encodes the spectrum of those fluctuations. Their survival tells us about the evolution of the universe over nearly 14 billion years, and they might be everywhere. In the dark matter halo surrounding the Milky Way, in the space between stars, in the voids between galaxies. Some of them feeding slowly on stray gas and dark matter, growing incrementally over cosmic timescales. Others dormant, drifting through empty space, waiting for something to fall within reach. A few of them might be close. Close enough that their gravity has a measurable effect on the orbits of objects we can see. Close enough that with the right instruments, the right surveys, the right analysis, we might finally detect them. Or they might not exist at all. The theory is sound, the physics allows it. But the universe does not care about what we think is elegant or plausible. It does what the initial conditions dictate. And if the early universe was not lumpy enough, if the density fluctuations were too weak or too smooth, then primordial black holes never formed. The mass spectrum would be empty. The only black holes in the universe would be the ones that formed from stars, and the mysteries we have been discussing, the early supermassive black holes, the missing dark matter, would need different explanations. That uncertainty is what makes this field so compelling. We are standing at the edge of a question that could reshape our understanding of the universe. If primordial black holes exist, they tie together half a dozen unsolved problems in cosmology and astrophysics. They explain the early supermassive black holes. They provide a natural dark matter candidate. They connect the quantum fluctuations of inflation to the large-scale structure of the universe. They give us a direct observational window into the first second after the Big Bang, a moment that is otherwise hidden behind an opaque wall of hot plasma. But if they do not exist, if the searches come up empty and the constraints keep tightening until there is no room left for primordial black holes to hide, then we are back to the drawing board. The mysteries remain. The early supermassive black holes still need an explanation. The dark matter is still undetected, and the universe once again has surprised us by refusing to behave the way we expected. For now, primordial black holes remain hypothetical. Survivors in theory, invisible in practice, spanning a mass range so vast that no other object in the universe comes close. From microscopic relics that evaporated before the universe finished its first breath to supermassive monsters that could outlive the stars themselves. If they are real, they are everywhere. If they are not, the universe has found a different way to build its structures and fill the dark spaces between the light. Either way, the answer will tell us something fundamental about how the cosmos works. We just have to find it. And that search, as it turns out, might depend on the one thing in the universe we have never directly detected but know is there. The invisible scaffolding that holds galaxies together and fills 85% of the mass budget of creation, dark matter. And if primordial black holes are real, they might be it. The universe weighs too much. That sentence sounds absurd on its face. How does the entire universe, the thing that contains all matter and energy and space and time, weigh more than it should? But that is exactly the problem. We have weighed the universe, not directly, obviously. You cannot put the cosmos on a scale, but we have measured how galaxies move, how clusters of galaxies hold together, how light bends around massive objects, and when we add up all the matter we can see, all the stars and gas and dust and planets, we come up about 85% short. The universe is behaving as if it contains roughly 6 times more matter than we can account for. And that missing matter, whatever it is, has been sitting in the dark for the entire history of the cosmos, holding galaxies together, shaping the flow of structure across billions of light years, and refusing to interact with light in any way we can detect. We call it dark matter, which is not a very creative name. It is dark because it does not emit light. It is matter because it has mass and exerts gravity. That is all we know for certain. Everything else, what it is made of, what particles compose it, whether it even is particles, remains one of the deepest unsolved mysteries in physics. And despite decades of effort, billions of dollars in detector technology, and some of the brightest minds on the planet throwing themselves at the problem, we have not found it. Not directly. We see its effects everywhere. We just cannot catch the thing itself. The evidence for dark matter is overwhelming. It shows up in so many independent observations, across so many different scales, that dismissing it as a mistake or a quirk of our models is no longer viable. The first hint came in the 1930s when astronomer Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast the galaxies were moving relative to each other and used that speed to estimate the total mass of the cluster. The logic is straightforward. The faster the galaxies move, the more mass the cluster needs to have to keep them from flying apart. When Zwicky did the math, he found that the cluster needed to be about 400 times more massive than the visible matter could account for. He called the missing mass dunkle materie, dark matter, and suggested that some invisible substance was filling the space between the galaxies. Nobody took him seriously. Zwicky had a reputation for being difficult, and his measurements were considered rough. The idea that most of the universe's mass could be invisible seemed too strange to be true, so the finding was filed away and largely ignored for 40 years. Then, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford measured the rotation curves of spiral galaxies. A rotation curve is a graph that shows how fast stars and gas are moving at different distances from the center of a galaxy. If most of a galaxy's mass is concentrated in the center, where the visible stars are brightest, then the stars farther out should be moving more slowly. This is the same principle that governs the solar system. Mercury orbits the Sun faster than Earth. Earth orbits faster than Jupiter. The farther you are from the central mass, the weaker the gravitational pull, and the slower you move. Rubin expected to see the same pattern in galaxies. Stars near the center should be moving fast. Stars at the edge should be moving slower. The rotation curve should drop off as you move outward. That is what Newtonian gravity predicts. That is what every physics textbook says should happen. The rotation curves did not drop off. They stayed flat. Stars at the edge of galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster. That should not be possible unless there is more mass farther out than the visible stars suggest. A lot more mass. Enough to keep the outer stars moving at speeds that would otherwise fling them out of the galaxy entirely. Rubin and Ford measured galaxy after galaxy. Same result. Flat rotation curves, every single one. The implication was unavoidable. Galaxies contain far more mass than we can see. That mass is not concentrated in the center where the stars are. It is spread out in a massive halo that extends well beyond the visible edge of the galaxy. And whatever it is made of, it does not emit light. It does not absorb light. It does not reflect light. It just sits there, invisible, holding the galaxy together with its gravity. That was the moment dark matter went from a fringe idea to a central problem, because if every galaxy is embedded in a halo of invisible matter, and those halos contain 6 times more mass than all the stars and gas combined, then most of the universe is made of something we have never detected. Something that does not show up in any telescope, no matter what wavelength you look at. Something that interacts with ordinary matter only through gravity. The evidence piled up. Gravitational lensing, the bending of light around massive objects, showed that galaxy clusters contain far more mass than their visible components suggest. The cosmic microwave background, the faint glow of radiation left over from the early universe, has patterns in it that only make sense if there was extra mass pulling on the gas in the early universe, amplifying the density fluctuations that would eventually become galaxies. Simulations of structure formation, the process by which galaxies and clusters assemble over billions of years, only match observations if you include dark matter. Without it, the structures form too slowly, too late. With it, everything falls into place. So we know dark matter is real. The question is what it is made of, and that is where the field has been stuck for the better part of 50 years. The leading candidates for dark matter are particles, not ordinary particles like protons and electrons, but exotic ones that have never been directly observed. Particles that were produced in the early universe shortly after the Big Bang and that have been drifting through space ever since, interacting with ordinary matter so weakly that we have not been able to catch them despite decades of trying. The most popular candidate for a long time was something called a WIMP, which stands for Weakly Interacting Massive Particle. The name is straightforward. These particles would be massive, meaning they have significant mass compared to something like an electron. And they would interact weakly, meaning they only feel the weak nuclear force and gravity. They would not interact electromagnetically, so they would not emit or absorb light. They would pass through ordinary matter, almost as if it were not there. A WIMP could pass through your body, through the Earth, through the Sun, and the odds of it actually hitting an atomic nucleus on the way through would be vanishingly small. WIMPs are appealing because they fit naturally into extensions of the standard model of particle physics. Theories like supersymmetry, which predict a whole zoo of new particles that mirror the ones we already know, include particles that have exactly the properties you would want for dark matter: massive, stable, weakly interacting, produced in the right quantities in the early universe to account for the observed dark matter abundance. The math worked, the predictions were testable. Physicists built detectors, and they came up empty. Decades of searches, detectors buried deep underground to shield them from cosmic rays. Tanks of liquid xenon chilled to near absolute zero, waiting for a WIMP to collide with a nucleus and produce a tiny flash of light. Particle colliders smashing protons together at high energies, hoping to create WIMPs in the debris. Satellites in orbit searching for the gamma rays that would be produced if WIMPs annihilated each other in the dense cores of galaxies. Experiment after experiment, each one more sensitive than the last. No detection. The parameter space for WIMPs has been squeezed tighter and tighter with each null result. The simplest versions of supersymmetry have been ruled out. The masses and interaction strengths that were once considered most likely are now excluded by the data. WIMPs are not dead as a hypothesis, but they are on life support. Another candidate is the axion. Axions are even more exotic than WIMPs. They are hypothetical particles that were originally proposed to solve a different problem in particle physics, something to do with why certain processes in quantum chromodynamics do not violate a symmetry they should respect. The details are not important. What matters is that axions, if they exist, would be incredibly light, far lighter than an electron, and they would be produced in enormous numbers in the early universe. A galaxy-sized halo of dark matter made of axions would contain something like 10 to the power of 70 particles, each one barely interacting with anything, but collectively contributing enough mass to explain the missing matter. Axions are harder to detect than WIMPs because they interact so weakly. The experiments designed to find them involve placing detectors in strong magnetic fields and looking for the faint radio signals that would be produced if axions convert into photons. The signal would be incredibly weak. The background noise is high. The searches have been running for years. A few experiments have reported hints of possible signals, but nothing conclusive, nothing that has been independently confirmed. The axion remains hypothetical. There are other candidates: sterile neutrinos, particles that interact even more weakly than ordinary neutrinos; primordial magnetic monopoles, hypothetical remnants from the early universe; dark photons, a kind of shadow counterpart to ordinary photons. Each one has its own theoretical motivation and its own set of experimental challenges, and each one, so far, has avoided detection. The null results are starting to feel like a pattern. We have been searching for dark matter particles for decades. We have built incredibly sensitive detectors. We have searched across a wide range of masses and interaction strengths, and we have found nothing. That does not mean the particles do not exist. It just means they are either much more elusive than we thought, or we have been looking in the wrong place, which brings us back to black holes. Because black holes are not particles, they are not exotic, they are not predicted by extensions of the standard model. They are just gravity, pure concentrated gravity, and gravity is the one thing we know dark matter has. So the question, the one that keeps bubbling up every time the particle searches come up empty, is whether dark matter could be black holes. Not stellar mass black holes, the ones that form from dying stars. We can account for those. We see them. We know how many there are. They do not add up to enough mass to explain dark matter. But primordial black holes, the ones that could have formed in the first moments after the Big Bang, before stars even existed, those are a different story. If primordial black holes formed in the early universe, and if they formed in the right numbers across the right mass range, they could contribute significantly to the dark matter budget. Maybe all of it, maybe just a fraction, but enough to matter, enough to show up in the observations, enough to explain why galaxies hold together the way they do. The idea is appealing for the same reason it is frustrating. Appealing because it solves the problem with ordinary physics. You do not need new particles. You do not need supersymmetry or axions or sterile neutrinos. You just need the early universe to have been lumpy enough to produce black holes from density fluctuations. That is allowed by general relativity. That is consistent with what we know about inflation and the primordial density spectrum. It is not exotic. It is just gravity doing what gravity does when you give it enough density in a small enough volume. Frustrating because black holes are invisible. A primordial black hole drifting through the galaxy does not emit light. It does not absorb light unless it happens to pass directly in front of a star. It does not interact with ordinary matter except through gravity. It is, for all practical purposes, the perfect dark matter candidate, which also makes it the perfect hiding place. If dark matter is made of primordial black holes, we would see exactly what we see: flat rotation curves, gravitational lensing, structure formation that matches the simulations. All the evidence for dark matter, with none of the electromagnetic signals that would let us identify what it actually is. The hypothesis that primordial black holes could be dark matter is not new. It has been around since the 1970s, proposed not long after Hawking's original paper on primordial black hole formation. For a long time, it was considered a fringe idea, interesting but unlikely. The mainstream view was that dark matter had to be particles because that is what the models predicted, and that is where the theoretical momentum was. But as the particle searches have continued to come up empty, the primordial black hole hypothesis has gotten a second look. Not because new evidence appeared, but because the old evidence for particles has not materialized. The challenge is constraints. If primordial black holes make up a significant fraction of the dark matter, they should leave observable signatures. Gravitational lensing is the most obvious one. When a massive object passes between us and a distant star, the object's gravity bends the star's light, causing the star to briefly brighten. This is called microlensing, and surveys have been conducted to look for these events in our own galaxy and in nearby galaxies. The surveys have found some microlensing events, but not enough to account for all the dark matter. The constraints from microlensing rule out primordial black holes as all of the dark matter in certain mass ranges, particularly between about 10 to the power of -7 solar masses and 10 solar masses. But the constraints are not uniform. They depend on the mass of the black holes and how they are distributed. In some mass ranges, the observational limits are tight. In others, they are loose. There are windows, gaps in the constraints, where a population of primordial black holes could still be hiding without violating any of the observations we have made so far. One such window sits around 10 to the power of -10 solar masses, roughly the mass of an asteroid. Black holes in that range would be too light to produce strong microlensing signals on the scales we have surveyed. Another window sits at much higher masses, around 10 to 100 solar masses. Primordial black holes in that range could be rare enough and spread out enough that they would not produce detectable microlensing events in the surveys conducted so far. The cosmic microwave background also provides constraints. Primordial black holes, if they were accreting gas in the early universe, would have heated the surrounding material and altered the temperature and polarization patterns in the CMB. Observations from satellites like Planck have been used to place limits on how many primordial black holes could have existed at different mass ranges. Again, the constraints rule out primordial black holes as all of the dark matter in many scenarios, but they do not rule them out completely. There is still room in the parameter space for a population of primordial black holes to contribute a fraction of the dark matter. The connection between primordial black holes and dark matter is not just about explaining the missing mass, it is about explaining the structure. Dark matter is not evenly distributed throughout the universe. It clumps, it forms halos around galaxies. It collects in the nodes of the cosmic web, the vast filamentary structure that spans billions of light years. The distribution of dark matter shapes the distribution of visible matter. Galaxies form in the densest regions of dark matter halos. Stars form in the gas that falls into those halos. The entire architecture of the universe, the way matter is organized on the largest scales, is dictated by the gravitational pull of dark matter. If dark matter is made of particles, those particles would have been moving fast in the early universe, smoothing out small-scale structure and allowing only the largest halos to form first. This is called cold dark matter, and it is the standard assumption in most cosmological models. Cold dark matter predicts a specific pattern of structure formation, with large halos forming first and smaller structures forming later as the halos fragment and merge. If dark matter is made of primordial black holes, the story is different. Black holes do not move fast. They do not smooth out structure the way fast-moving particles do. A primordial black hole is a point mass, a gravitational anchor that sits in place and pulls matter toward it. If the early universe contained a population of primordial black holes, they would have acted as seeds. The first structures would have formed around them. Gas would have collapsed into their gravitational wells. Stars would have ignited in the densest regions. Galaxies would have assembled faster than they would have in a purely particle-based dark matter scenario. This is one of the reasons primordial black holes have gotten more attention in recent years. Because the observations, particularly the ones from the James Webb Space Telescope, keep showing us galaxies and supermassive black holes that formed earlier than the standard models predict. If dark matter is made of primordial black holes, that early structure formation is not a mystery. It is exactly what you would expect. The black holes were already there, waiting in the dark, providing the gravitational wells that accelerated the collapse of gas and the formation of the first stars. The idea that primordial black holes could seed galaxy formation is not just speculation. Simulations have been run to test the hypothesis. When you seed a cosmological simulation with a population of primordial black holes instead of particle dark matter, the structures form faster, galaxies appear earlier, supermassive black holes grow more quickly, the timeline compresses, and the results start to look more like what we actually observe at high redshifts. That does not prove primordial black holes are dark matter. It just shows that the hypothesis is consistent with the observations. which is more than you can say for some of the particle dark matter models that have struggled to explain the early massive galaxies and black holes. There is another piece of the puzzle that ties into this: gravitational waves. When two black holes merge, they produce ripples in space-time that propagate outward at the speed of light. We have been detecting those ripples since 2015 with observatories like LIGO and Virgo. Most of the black hole mergers we have detected involve black holes in the range of a few to a few dozen solar masses. Stellar mass black holes, the kind that form from collapsing stars. But some of the mergers have involved black holes that are heavier than we expect from stellar processes. Black holes weighing 40, 50, even 70 solar masses. Those are at the upper edge of what stellar collapse should be able to produce. One explanation for those heavy black holes is that they are primordial. If a population of primordial black holes exists in the mass range of 10 to 100 solar masses, they would occasionally collide and merge. The merger rate would depend on how densely they are packed and how fast they are moving relative to each other. If primordial black holes make up a significant fraction of the dark matter in galaxies, the merger rate could be high enough to explain some of the events LIGO has detected. This is testable. If the black hole mergers LIGO is seeing are primordial, their statistical properties should be different from mergers involving stellar black holes. Primordial black holes would not have the same mass distribution as stellar black holes. They would not have the same spins. They would not be preferentially located in regions with active star formation. Surveys are underway to analyze the population of black holes detected by gravitational wave observatories and determine whether any of them could be primordial. The results so far are inconclusive. Some of the detected black holes fit the profile, others do not. The data set is still small, but as more mergers are detected, the statistics will improve, and we will get a clearer picture of whether primordial black holes are contributing to the population. The search for primordial black holes as dark matter is not limited to gravitational waves. Other methods are being explored. One involves looking for the effects of primordial black holes on the orbits of stars in the galaxy. If a primordial black hole passes close to a star, the gravitational tug will slightly alter the star's trajectory. Over time, those small perturbations accumulate. If we have precise enough measurements of stellar positions and velocities, we might be able to detect the influence of passing primordial black holes. Surveys like Gaia, which is mapping the positions and motions of over 1 billion stars in the Milky Way, are providing the data needed for these kinds of searches. Another method involves looking for the lensing effects of primordial black holes on distant quasars or stars. If a primordial black hole passes in front of a distant light source, the light gets bent, producing a characteristic brightening pattern that can be distinguished from other types of variability. Surveys monitoring millions of stars in nearby galaxies are searching for these micro-lensing events. So far, the number of detected events is lower than you would expect if primordial black holes made up all the dark matter, but not low enough to rule them out completely. The constraints keep tightening, but the hypothesis remains viable in certain mass ranges. There is also the possibility that primordial black holes could be detected indirectly through their effects on the cosmic microwave background or through the radiation they produce if they are accreting gas. A primordial black hole sitting in a dense region of the early universe would pull in gas, heat it up, and produce X-rays or other high-energy radiation. That radiation could leave faint imprints on the CMB or contribute to the diffuse background radiation we observe today. Searches for these signals are ongoing, but the expected signals are faint and hard to disentangle from other sources of background radiation. The bottom line is that primordial black holes as dark matter remains an open question. The hypothesis has not been proven, but it has not been ruled out either. The constraints are tight in some mass ranges and loose in others. There are windows where primordial black holes could still be contributing a significant fraction of the dark matter without violating any observations, and the fact that decades of searching for particle dark matter have come up empty has kept the black hole hypothesis alive. If primordial black holes are dark matter, or even part of it, the implications are profound. It would mean that the majority of the matter in the universe is not made of particles, it is made of gravity. Pure concentrated gravity in the form of black holes that formed before the first stars, before the first atoms, before anything we recognize as structure. It would mean that the dark matter halos surrounding galaxies are not diffuse clouds of exotic particles, but populations of invisible black holes scattered throughout the halo, pulling on the visible matter, shaping the rotation curves, anchoring the formation of galaxies and stars. It would also mean that some of those black holes could be close, very close, drifting through the Milky Way, passing within light years or even light months of the solar system. Invisible, undetectable by most instruments, producing no light, no heat, no radiation, just gravity. A primordial black hole with a mass of 10 solar masses could be sitting a few light years from Earth right now, and we would have no way of knowing unless it happened to pass close enough to a star or planet to produce a measurable gravitational disturbance. That is unsettling. Not because such a black hole would pose any danger. The odds of a direct collision are astronomically low, but because it drives home just how little we actually know about what is out there in the dark. We have mapped the positions of billions of stars. We have catalogued thousands of exoplanets. We have traced the large-scale structure of the universe across billions of light years, and yet 85% of the matter that makes up that structure is completely invisible to us. We know it is there because we can see its gravitational effects. We just do not know what it is. Primordial black holes offer one answer, not the only answer, maybe not even the right answer, but an answer that fits the observations, that solves multiple problems at once, and that does not require inventing new physics or new particles. It just requires the early universe to have been lumpier than we thought, to have produced density fluctuations sharp enough to collapse into black holes before the first stars ignited. And if that happened, if those black holes scattered themselves across the cosmos and survived for billions of years, then the dark matter we have been searching for might not be hiding in some exotic particle we have not discovered yet. It might be hiding in plain sight, or rather, in plain darkness, as black holes that have been sitting in the universe since the beginning, waiting for us to figure out how to see them. The search is ongoing, the constraints are tightening, the observations are improving. And with every new gravitational wave detection, every new microlensing survey, every new analysis of the cosmic microwave background, we are narrowing the parameter space where primordial black holes could be hiding. If they are out there, we will find them. If they are not, the null result will tell us something just as important. That dark matter is not black holes, that the missing mass is something else entirely, something we have not thought of yet, something that will require new physics, new experiments, new ideas to uncover. But until we know for sure, primordial black holes remain one of the most compelling candidates for dark matter, a hypothesis born in the first instant after the Big Bang, a population of invisible objects that could be filling the space between stars, holding galaxies together, shaping the structure of the universe. And the only way to confirm or rule them out is to keep looking, to keep searching for the faint gravitational whispers, the subtle lensing effects, the rare collisions that would reveal their presence, the echoes of objects that formed before anything else, before light, before atoms, before time itself had stretched far enough for the universe to take a breath. If those echoes are out there, we are getting close to hearing them. The universe is not required to make things easy for us. That might be the most important lesson you learn if you spend any time in observational astronomy. We build telescopes powerful enough to see back to the edge of time. We design detectors sensitive enough to feel the vibrations of colliding black holes a billion light-years away. We point instruments at the sky and collect data with precision that would have seemed like magic a generation ago, and still, most of what we are looking for stays hidden. Not because it is not there, but because nature has a habit of burying its most interesting secrets under layers of noise, distance, and sheer improbability. Primordial black holes, if they exist, are buried deeper than most. They do not glow. They do not emit radio waves or X-rays unless they happen to be feeding, and a primordial black hole drifting through empty space has nothing to feed on. They do not leave trails. They do not cluster in convenient locations where we can point a telescope and take a census. They are scattered across the cosmos, invisible, silent, detectable only through the faint gravitational whispers they leave behind when they interact with something we can actually see. Finding them is not impossible, but it requires patience, cleverness, and a willingness to search for signals so subtle that most people would dismiss them as noise. The search for primordial black holes has been going on for decades, and the tools have gotten better with time. Early efforts were crude, limited by the sensitivity of the instruments and the small size of the data sets. Modern searches use satellite observatories, gravitational wave detectors, and surveys that monitor millions of stars simultaneously, looking for the faint flicker that might indicate a black hole passing in front of a distant light source. The searches have not found a smoking gun, not yet, but they have tightened the constraints, narrowed the parameter space, and in the process revealed just how elusive these objects are. The most straightforward way to detect a primordial black hole is through gravitational lensing. The principle is simple. Light travels in straight lines through flat space, but space is not flat when there is mass around. Mass warps space-time, and light follows the curves. When a massive object passes between you and a distant light source, the object's gravity bends the light, acting like a lens. If the alignment is just right, the light from the background source gets focused, and the source appears brighter. The effect is called gravitational lensing, and it is one of the most powerful tools we have for detecting invisible mass. There are different types of gravitational lensing, depending on the scale. Strong lensing happens when a massive galaxy or galaxy cluster sits between us and a more distant galaxy. The foreground mass distorts the background galaxy's light into arcs or multiple images. We have seen this countless times. It is dramatic, unmistakable, and relatively easy to model. Weak lensing is subtler. It involves the statistical distortion of thousands of background galaxies caused by the large-scale distribution of mass along the line of sight. Astronomers use weak lensing to map dark matter on cosmic scales, tracing the invisible scaffolding that holds the universe together. Microlensing is different. It happens when a relatively small, compact object, something like a star or a black hole, passes in front of a more distant star. The foreground object's gravity bends the light from the background star, and for a brief period, the background star appears brighter. The brightening is smooth, symmetric, and temporary. The light curves. The graphs that show how the star's brightness changes over time have a characteristic shape: a slow rise, a peak, and a slow decline, all perfectly symmetric if the lensing object passes directly in front of the star. The duration of the event depends on the mass of the lensing object and how fast it is moving. A low-mass object produces a short event lasting days or weeks. A higher mass object produces a longer event lasting months. Microlensing is ideal for detecting primordial black holes because it does not require the black hole to be doing anything special. It does not need to be feeding. It does not need to be near a star or a gas cloud. It just needs to pass between us and a background star, and the geometry does the rest. If primordial black holes exist, and they are scattered throughout the dark matter halo of our galaxy, then occasionally, by pure chance, one of them should drift in front of a star in a nearby galaxy, produce a microlensing event, and give itself away. The challenge is that microlensing events are rare and unpredictable. You cannot point a telescope at a specific patch of sky and expect to see one. You have to monitor millions of stars simultaneously, night after night, and wait for the rare moment when a lensing object happens to pass in front of one of them. That requires large surveys, automated data collection, and sophisticated algorithms to sift through the noise and identify the handful of real events buried in mountains of data. Two major surveys tackled this problem in the 1990s and early 2000s. One was called EROS, which stands for Expérience pour la recherche d'objets sombres, or Experiment for Research of Dark Objects. The other was called MACHO, which stands for Massive Compact Halo Objects, a term that includes primordial black holes, brown dwarfs, and any other dark, compact mass that might be lurking in the galactic halo. Both surveys monitored millions of stars in the Large Magellanic Cloud and the Small Magellanic Cloud, two small galaxies orbiting the Milky Way. The idea was that if the Milky Way's dark matter halo contained a significant population of primordial black holes, some of them would occasionally pass in front of stars in the Magellanic Clouds and produce detectable microlensing events. The surveys ran for years. EROS monitored about 33 million stars. MACHO monitored roughly 11 million. The data collection was relentless. Automated telescopes taking images night after night, software pipelines processing the images, flagging anything that looked like it might be a lensing event and sending it to human analysts for confirmation. The surveys found microlensing events. Not many, but some. A few dozen candidates across both surveys. Enough to show that the technique worked, not enough to explain the dark matter. When the results were analyzed, the conclusion was clear. If the microlensing events detected by EROS and MACHO were caused by compact objects in the galactic halo, those objects could account for at most a few percent of the dark matter, not 50%, not 20%, a few percent. The surveys placed tight constraints on the abundance of primordial black holes in certain mass ranges, particularly between about 1/10,000,000th of a solar mass and 10 solar masses. In that range, if primordial black holes made up a significant fraction of the dark matter, the surveys should have seen far more events than they did. The fact that they did not rule out primordial black holes as the dominant form of dark matter in those mass windows, that result was disappointing for proponents of the primordial black hole hypothesis, but it was not the end of the story. The constraints from microlensing surveys are strong, but they are not absolute. They depend on assumptions about where the primordial black holes are located, how fast they are moving, and how they are distributed throughout the halo. If the distribution is clumpy rather than smooth, or if the black holes are concentrated in regions that were not covered by the surveys, the constraints weaken. And crucially, the constraints only apply to certain mass ranges. Below about 1/10,000,000th of a solar mass, the microlensing events would be too short to detect with the cadence and sensitivity of the EROS and MACHO surveys. Above about 10 solar masses, the events would be so rare that even a large survey might miss them. The surveys closed some doors, but they left others open. More recent microlensing efforts have continued the search with better instruments and larger data sets. The OGELE survey, short for Optical Gravitational Lensing Experiment, has been running since the early 1990s and has expanded to monitor over 1 billion stars in the Milky Way's bulge and the Magellanic Clouds. OGEL has detected thousands of microlensing events, though most of them are attributed to ordinary stars rather than black holes. A handful of events have unusual characteristics, long durations or asymmetric light curves that hint at more massive or exotic lensing objects, but none of the events provide definitive proof of primordial black holes. The results remain consistent with a dark matter halo that contains mostly particles or very low-mass compact objects, not a large population of black holes in the mass range where microlensing is most sensitive. Gravitational lensing is not the only way to search for primordial black holes. Another approach involves gravitational waves. When two black holes orbit each other, they lose energy by radiating gravitational waves, ripples in space-time that propagate outward at the speed of light. As the black holes lose energy, their orbit tightens and they spiral inward. Eventually, they collide and merge, releasing a final burst of gravitational waves so powerful that it can be detected across billions of light years. Since 2015, observatories like LIGO and Virgo have been detecting these mergers, opening an entirely new window into the universe. Most of the black hole mergers detected so far involve stellar mass black holes, objects weighing a few to a few dozen solar masses. These are consistent with black holes that formed from collapsing stars. But a few of the detected mergers have involved unusually heavy black holes, weighing 40, 50, or even 70 solar masses. Those masses are at the upper edge of what stellar collapse is expected to produce. Some astrophysicists have suggested that these heavy black holes might be primordial rather than stellar in origin. If a population of primordial black holes exists in the mass range of 10 to 100 solar masses, they would occasionally collide and merge, and the resulting gravitational wave signal would look very similar to the signals from stellar black hole mergers. The challenge is distinguishing primordial black hole mergers from stellar ones. The gravitational wave signal itself does not carry a label saying this came from a primordial black hole or this came from a stellar black hole. The waveform is determined by the masses and spins of the merging objects, and those properties can overlap between stellar and primordial populations. What you need to look for are statistical differences in the population. Primordial black holes would not have the same mass distribution as stellar black holes. They would not be preferentially located in regions with active star formation. Their spins might be different, randomly oriented rather than aligned with the orbital plane of a binary system. If you can collect enough merger events and analyze the population as a whole, you might be able to identify a subpopulation that does not fit the stellar formation pathway. LIGO and Virgo have detected dozens of black hole mergers so far, and the data set is growing with every observing run. The population shows a lot of variety. Some black holes are spinning fast, others slowly. Some mergers involve black holes of similar mass, others involve mismatched pairs. A few mergers have produced remnants that are heavier than expected, raising questions about how such massive black holes could have formed in the first place. Researchers are analyzing the data to see if any subset of the detected mergers shows the characteristics you would expect from primordial black holes. The results so far are inconclusive. Some mergers fit the profile, others do not. The statistics are still too weak to make a definitive claim. One intriguing possibility is that future gravitational wave detectors, instruments like the planned space-based observatory LISA or next-generation ground-based detectors, will be sensitive enough to detect mergers involving lower-mass black holes. LIGO and Virgo are most sensitive to black holes in the range of a few to a few hundred solar masses, LISA will be sensitive to black holes in the range of thousands to millions of solar masses, the supermassive black holes at the centers of galaxies. But there is a gap in between, a mass range where neither current nor planned detectors are optimized. If primordial black holes exist in that gap, they might remain hidden from gravitational wave searches for years to come. Another search strategy involves looking for Hawking radiation from evaporating primordial black holes. As we discussed earlier, black holes radiate energy through quantum effects near the event horizon, and small black holes radiate faster than large ones. A primordial black hole with a mass around 10 to the power of 12 kilograms would be finishing its evaporation right now, releasing a final burst of high-energy gamma rays as it disappears. If such an event happened nearby, within a few light years of Earth, the gamma ray flash would be detectable with current instruments. Satellites like the Fermi Gamma Ray Space Telescope have been searching for these signals. The expected signature is a brief, intense burst of gamma rays with a specific energy spectrum that matches the predictions of Hawking radiation. The challenge is distinguishing evaporating black holes from other gamma ray sources. The universe is full of gamma ray bursts, most of them caused by distant supernovae or colliding neutron stars. The bursts from evaporating primordial black holes would have a different energy profile, but the differences are subtle and the background noise is high. So far, no gamma-ray bursts have been definitively attributed to evaporating primordial black holes. That does not mean they are not happening. It just means that if they are either very rare or the signals are too faint or too brief to stand out against the background. The lack of detections places constraints on the number of primordial black holes in the mass range where evaporation is happening now. If there were a large population of such black holes in the local universe, we should have seen multiple gamma-ray bursts by now. The fact that we have not suggests that primordial black holes in that mass range are either very rare or they have already evaporated in regions of space that are not well covered by current surveys. The cosmic microwave background provides another powerful constraint on primordial black holes. The CMB is the faint glow of radiation left over from about 380,000 years after the Big Bang, the moment when the universe cooled enough for atoms to form and photons to travel freely. The temperature and polarization patterns in the CMB are incredibly uniform, varying by only about 1 part in 100,000 from one patch of sky to another. Those tiny variations encode information about the density fluctuations in the early universe, the seeds that would eventually grow into galaxies and clusters. Primordial black holes, if they existed in the early universe, would have affected the CMB in several ways. First, they would have contributed to the overall density of matter, altering the balance between matter and radiation and changing the predicted patterns in the CMB. Second, if the primordial black holes were accreting gas, they would have heated the surrounding material, injecting energy into the early universe and altering the ionization history that would leave imprints in the CMB's temperature and polarization maps, subtle distortions that could be detected with sensitive enough instruments. The Planck satellite, which mapped the CMB with unprecedented precision, has been used to place constraints on the abundance of primordial black holes. The results show that if primordial black holes were accreting gas in the early universe, they could only make up a small fraction of the dark matter. The constraints are strongest for black holes in the mass range, where accretion would have been most efficient, roughly between a few solar masses and a few thousand solar masses. In that range, the energy injection from accreting black holes would have been large enough to produce detectable distortions in the CMB. The fact that those distortions are not seen in the data rules out a large population of primordial black holes in that mass window. But again, the constraints are not absolute. They depend on assumptions about how efficiently primordial black holes accreted gas and how that accretion affected the surrounding environment. If the accretion was less efficient than the models assume, or if it was concentrated in regions that did not significantly affect the global ionization history, the constraints weaken, and as with microlensing, there are gaps in the mass spectrum where the CMB constraints are less tight. Very low-mass primordial black holes, ones that would have evaporated before the CMB was released, would not have left any imprint. Very high-mass primordial black holes, ones that were too rare or too isolated to significantly affect the ionization history, might also have avoided detection. The picture that emerges from all these searches is one of a tightly constrained but not entirely closed hypothesis. Primordial black holes, if they exist, cannot make up all of the dark matter in most mass ranges. The microlensing surveys rule them out as the dominant component in the range from about 1/10,000,000th of a solar mass to 10 solar masses. The CMB constraints rule them out in the range from a few solar masses to a few thousand solar masses, at least if they were accreting gas efficiently. The gamma-ray searches rule out large populations in the mass range where evaporation is happening now, and the gravitational wave detections have not yet provided clear evidence for a primordial population, though the dataset is still growing, but there are still windows. Gaps in the constraints where primordial black holes could be hiding. One such window sits at very low masses, around 10 to the power of 17 grams, roughly the mass of a small asteroid. Black holes in that range would be too light to produce strong microlensing signals, too heavy to have evaporated yet, and too isolated to have significantly affected the CMB. Another window sits at higher masses, around 10 to 100 solar masses, where the microlensing constraints are weaker and the gravitational wave population is still being characterized. A third window might exist at even higher masses, thousands or tens of thousands of solar masses, where primordial black holes could have seeded the formation of supermassive black holes without violating any of the existing constraints. The search strategies are evolving. New microlensing surveys are being planned, with better sensitivity and longer baselines, capable of detecting shorter events and probing lower mass objects. Next-generation gravitational wave detectors will expand the observable mass range and improve the statistics on black hole mergers, making it easier to identify unusual populations. Future CMB experiments will map the polarization patterns with even greater precision, tightening the constraints on energy injection in the early universe. And gamma-ray observatories will continue monitoring the sky, searching for the faint flashes that would signal the final moments of an evaporating primordial black hole. One of the most promising future search strategies involves looking for the effects of primordial black holes on the orbits of objects in the solar system. If a primordial black hole passed through the solar system or nearby interstellar space, its gravity would tug on the planets, asteroids and comets, slightly altering their orbits. The changes would be tiny, fractions of a percent, but they would accumulate over time. Missions like Gaia, which is mapping the positions and motions of over 1 billion stars in the Milky Way, are providing the precision needed to detect these kinds of perturbations. If the data shows unexplained deviations in the orbits of nearby stars or solar system objects, primordial black holes could be one explanation. Another approach involves searching for the gravitational effects of primordial black holes on the distribution of stars in the galaxy. If a population of heavy primordial black holes exists in the galactic halo, their gravity would create subtle patterns in how stars move and cluster. By analyzing the kinematics of millions of stars, astronomers might be able to detect the influence of an invisible population of black holes pulling on the visible matter. This kind of analysis requires enormous datasets and sophisticated modeling, but the tools are getting better every year. There is also the possibility of detecting primordial black holes through their effects on the intergalactic medium, the diffuse gas that fills the space between galaxies. If a primordial black hole passed through a region of gas, it would heat the gas along its path, leaving a trail that could be detected in X-ray or radio observations. The trails would be faint and short-lived, but with sensitive enough instruments and large enough surveys, they might be detectable. The challenge in all of these searches is that primordial black holes, if they exist, are hiding in plain sight. They do not announce themselves. They do not flash or beep or leave obvious marks. They just sit in the dark, exerting gravity, occasionally interacting with something visible, and producing signals so subtle that they can easily be mistaken for noise or attributed to other sources. Finding them requires patience, clever analysis, and a willingness to look at the same data in new ways, searching for patterns that no one has thought to look for before. The searches have not found a smoking gun yet, but they have not come up empty either. Every constraint, every null result, every tightening of the parameter space tells us something about where primordial black holes could be and where they could not. The hypothesis is being refined, sharpened, tested against the data. And with every new observation, every new survey, every new detector that comes online, the search gets a little more sensitive, a little more precise, and a little closer to an answer. If primordial black holes exist, they are out there right now, drifting through the galaxy, scattered across the cosmic web, occasionally passing close enough to a star or a planet to leave a faint gravitational trace, occasionally colliding with each other and sending ripples through space-time, occasionally, in the case of the smallest ones, evaporating in a brief flash of gamma rays that no one happens to be watching. They are the echoes of the first instant after the Big Bang, the fossils of a moment when the universe was so young and so dense that gravity alone could carve out permanent structures from the chaos. And if we can learn to hear those echoes, to detect those fossils, to see the invisible objects that have been shaping the universe since before the first stars ignited, we will have opened a window into a moment that no telescope can ever directly observe, the first second, the first black holes, the first seeds of everything that came after. That story is still being written, the searches are still ongoing, and the universe, patient as always, is waiting for us to catch up. The universe does not have to explain itself to us. That might be the most humbling realization you come to after spending enough time staring at data from distant galaxies and early black holes. We ask questions, we build models, we point telescopes at the edge of the observable universe and collect photons that have been traveling toward us for more than 13 billion years. And the universe, patient as always, gives us answers, sometimes. But those answers do not always come in the form we expect, and they almost never come without raising a dozen new questions in the process. We started this story in the first fraction of a second after the Big Bang, in a moment so brief and so violent that the equations we use to describe reality start breaking down when you try to push them backward past that point. A universe with no stars, no atoms, no structure of any kind. Just density fluctuations, quantum noise stretched to cosmic scales by inflation, and gravity beginning the slow patient work of pulling overdense regions inward. From that chaos, from those first wrinkles in space-time, we proposed that black holes could have formed. Not from collapsing stars, because there were no stars yet. Just from gravity acting on density peaks sharp enough to overcome the expansion of space and collapse into singularities wrapped in event horizons, primordial black holes. The hypothesis is elegant in its simplicity and frustrating in its elusiveness. Elegant because it solves multiple problems at once without requiring exotic new physics. Frustrating because after 50 years of searching, we still have not found one, not definitively, not with the kind of ironclad evidence that lets you close the book and move on to the next mystery. The searches have tightened the constraints, ruled out large populations in certain mass ranges, and left open a handful of windows where primordial black holes could still be hiding. But they have not delivered a smoking gun, no gamma-ray flash from an evaporating black hole, no unambiguous gravitational wave signal from a primordial merger, no micro-lensing event that could not be explained by an ordinary star drifting across our line of sight. That does not mean primordial black holes do not exist. Absence of evidence is not evidence of absence, and the universe is under no obligation to make its secrets easy to uncover. What it means is that if primordial black holes are out there, they are either very rare, confined to mass ranges we have not yet been able to probe effectively, or distributed in ways that make them hard to distinguish from other dark compact objects. The hypothesis remains open. The searches continue, and the implications, if primordial black holes turn out to be real, are profound enough that the effort is worth it. Because primordial black holes are not just a curiosity. They are not just an exotic prediction from early universe cosmology that might or might not correspond to anything real. If they exist, they are woven into the structure of the cosmos at the most fundamental level. They are the oldest objects in the universe, the first permanent structures, the anchors around which everything else assembled, and their influence, whether we have detected them directly or not, might extend from the first galaxies to the dark matter halos surrounding every galaxy today, including our own. Let's start with what we know for certain. The universe contains supermassive black holes, millions of them, sitting at the centers of galaxies, weighing anywhere from a few million to tens of billions of solar masses, shaping the dynamics of their host galaxies, regulating star formation through powerful jets and winds, and occasionally lighting up as quasars when they feed on infalling gas. These are not hypothetical objects. We have seen them. We have measured their masses. We have watched them consume stars and tear apart gas clouds. We have even imaged the event horizon of one, the black hole at the center of the galaxy Messier 87, using the Event Horizon Telescope in 2019. Supermassive black holes are real, they are everywhere, and their existence raises a question that has been nagging at astronomers for decades. How did they get so big, so fast? The question became urgent when telescopes started finding supermassive black holes in galaxies that formed less than 1 billion years after the Big Bang. Not small black holes, not modest ones, monsters. Black holes weighing hundreds of millions of solar masses, sometimes billions, sitting in galaxies so young that the standard models said they should barely have had time to form stars, let alone grow black holes to such absurd sizes. The James Webb Space Telescope has made the problem worse, or better depending on your perspective, by finding even more of these early monsters. Quasars blazing at redshifts corresponding to less than 700 million years after the Big Bang. Black holes weighing tens of millions of solar masses when the universe was less than 5% of its current age. The timeline does not work. A stellar mass black hole, the kind that forms from a collapsing star, starts with a mass of maybe 10 to 100 solar masses. To grow to 1 billion solar masses, it needs to feed constantly. At the maximum rate physics allows, a rate called the Eddington limit. And even then, it takes about 1 billion years of non-stop feeding to reach that size. The early supermassive black holes did it faster, much faster. Which means either they were growing at super Eddington rates, violating or bending the rules we thought applied to accretion, or they did not start small. They started with a head start, A seed that was already massive enough that reaching 1 billion solar masses in a few 100 million years was merely difficult rather than impossible. Primordial black holes provide that head start. If a population of primordial black holes formed in the first second after the Big Bang, with masses ranging from thousands to hundreds of thousands of solar masses, they would have been sitting in the early universe long before the first stars ignited. When the first dark matter halos began to collapse and pull in gas, those primordial black holes would already have been there, embedded in the densest regions, acting as gravitational anchors. The gas would have flowed into their gravitational wells, stars would have formed around them, and the black holes would have started feeding, growing steadily over hundreds of millions of years. By the time the universe was 1 billion years old, a primordial seed that started at 100,000 solar masses could have grown to tens of millions or even hundreds of millions of solar masses. Scale up the seed mass or push the accretion rate slightly higher, and you can reach 1 billion solar masses without breaking the physics. This is the seed hypothesis. The idea that at least some of the supermassive black holes we see today, particularly the early ones, did not grow from stellar remnants. They grew from primordial seeds, black holes that formed before stars, before atoms, before anything we recognize as structure, and that have been growing ever since. The hypothesis solves the timeline problem. It explains how black holes could be so massive so early, and it ties the existence of supermassive black holes directly to the conditions in the first moments after the Big Bang, making them fossils of the universe's infancy rather than byproducts of stellar evolution. The evidence for this connection is still circumstantial, but it is mounting. Observations from the James Webb Space Telescope and the Chandra X Ray Observatory have identified black holes in the early universe that appear to be fully formed, sitting at the centers of young galaxies, already weighing tens of millions of solar masses. One such black hole, in a galaxy called U-Heads 1, was detected at a distance of about 13.2 billion light-years, meaning we are seeing it as it existed roughly 470 million years after the Big Bang. The black hole weighs about 10 times as much as the one at the center of the Milky Way. Another system, QS01, contains a black hole weighing around 50 million solar masses, detected at about 750 million years after the Big Bang. These are not anomalies. They are part of a growing population of early supermassive black holes that the standard models struggle to explain. Researchers have suggested that black holes in the early universe were not just passive passengers in galaxy formation. They were active participants. A study analyzing data from NASA's Spitzer Space Telescope and other infrared observatories found that black holes in the period between 400 and 800 million years after the Big Bang were responsible for at least 20% of the cosmic infrared background, the diffuse glow of infrared light that fills the universe. That is a significant fraction. It suggests that black holes were not rare curiosities in the early universe. They were common, widespread, and energetically important. Alexander Kashlinsky from NASA's Goddard Space Flight Center, who led the study, noted that the black holes appeared to be well established by that point in time, implying they had already been growing for a while. If they had already been growing, they needed seeds that were in place even earlier. And if those seeds were primordial, the timeline finally makes sense. Primordial black holes do more than explain the early supermassive population. They change the story of galaxy formation itself. In the standard picture, galaxies form when gas collapses into dark matter halos, cools, fragments, and ignites stars. The stars live, die, and enrich the gas with heavy elements. Over time, the galaxy builds up mass, structure, and complexity. Black holes enter the picture later, either as remnants of the first massive stars or as secondary products of gas collapsing directly into black holes in rare, finely tuned conditions. The black hole and the galaxy grow together, but the galaxy comes first. The black hole is a consequence, not a cause. If primordial black holes seeded galaxy formation, the order flips. The black hole comes first. It is already there, sitting in the densest region of a collapsing dark matter halo, pulling in gas, heating the surrounding material, and creating the gravitational well that accelerates the collapse of the gas cloud. Stars form around the black hole. The galaxy assembles itself in the black hole's gravitational field. The black hole is not a byproduct, it is the foundation, the seed from which the galaxy grows. This shift in perspective is subtle but profound. It suggests that the universe's largest structures, the galaxies that fill the cosmic web and the clusters that bind them together, owe their existence in part to objects that formed in the first instant after the Big Bang. Objects that were not made of stars or gas or anything we can see. Just gravity. Pure concentrated gravity stamped into existence by the density fluctuations left over from inflation. If that is true, then primordial black holes are not a footnote in the history of the cosmos. They are one of the opening chapters. The influence of primordial black holes extends beyond supermassive black holes and early galaxies. They might also be part of the dark matter. Not all of it, almost certainly. The constraints from microlensing surveys and the cosmic microwave background rule out primordial black holes as the dominant component of dark matter in most mass ranges. But they do not rule them out as a contributing fraction. A population of primordial black holes in the right mass windows spread throughout the galactic halo could account for 10 or 20% of the dark matter. Maybe less, maybe more in certain regions. Enough to matter. Enough to affect the dynamics of galaxies, the clustering of matter, the formation of structure on large scales. If primordial black holes make up even a small fraction of the dark matter, their gravitational influence would be everywhere. They would pull on the gas and stars in galaxies, shaping rotation curves, altering the distribution of mass, creating subtle patterns in how matter flows and clusters. They would pass through the solar system occasionally, tugging on planets and asteroids with their gravity, leaving faint traces that might one day be detected in the precision measurements of stellar and planetary orbits. They would merge with each other, producing gravitational wave signals that observatories like LIGO and Virgo are beginning to detect. And they would anchor the formation of the first structures, the seeds around which the cosmic web assembled. The hypothesis ties together multiple observations that have puzzled astronomers for years. The early supermassive black holes, the missing dark matter, the surprisingly rapid formation of galaxies in the first billion years, the gravitational wave signals from merging black holes that are heavier than stellar models comfortably predict. Each of these observations, taken alone, can be explained with enough creativity and willingness to stretch the standard models. Taken together, they point towards something missing in our understanding of the early universe. Primordial black holes are not the only possible explanation, but they are one of the few that addresses all of these puzzles at once, without requiring entirely new physics. The challenge, as always, is proof. The searches have been going on for decades, and the tools have improved dramatically. Microlensing surveys monitor millions of stars, watching for the brief brightening that signals a compact object passing in front of a background light source. Gravitational wave detectors listen for the ripples in space-time produced by merging black holes. Gamma-ray observatories scan the sky for the flashes that would signal an evaporating primordial black hole in its final moments. Satellites map the cosmic microwave background with extraordinary precision, searching for the faint distortions that would reveal energy injection from accreting black holes in the early universe. Each search narrows the parameter space, tightens the constraints, and pushes the hypothesis into narrower and narrower windows. But the windows have not closed. There are still gaps. Mass ranges where a population of primordial black holes could be hiding without violating any of the observations we have made so far. Very low masses, around 10 to the power of 17 grams, roughly the mass of a small moon. Very high masses, around 10 to 100 solar masses, where the microlensing constraints are weaker and the gravitational wave population is still being characterized. And intermediate masses, where the constraints from different methods do not yet overlap cleanly enough to rule out all possibilities. The searches are ongoing, the data sets are growing, and with every new observation, every new constraint, we get a little closer to an answer. The answer, when it comes, will tell us something fundamental about the universe. If primordial black holes exist, they are the oldest objects we know of, older than stars, older than galaxies, older than the cosmic microwave background. They formed in the first fraction of a second after the Big Bang, carved out of the density fluctuations that inflation left behind, and they have been drifting through space ever since, silent witnesses to the entire history of creation. Their masses encode the details of the primordial density spectrum. Their distribution encodes the physics of the early universe, the moment when gravity first locked onto overdense regions and pulled them into permanent structures. Detecting them would open a window into a moment we cannot observe any other way. The first second, the moment when the universe transitioned from a featureless expanding plasma into something with structure, with objects, with boundaries. If primordial black holes do not exist, that is also an answer. It tells us that the early universe was smoother than we thought, that the density fluctuations, while present, were not sharp enough or strong enough to produce black holes directly. It tells us that supermassive black holes grew from stellar seeds or direct collapse, that dark matter is made of particles we have not detected yet, and that the early formation of massive galaxies requires some other mechanism we have not fully accounted for. Either way, the search is worth it. Because the question is not just about black holes, it is about the nature of the early universe, the conditions that shaped the first structures, the processes that determined how matter would cluster and flow and assemble into galaxies over billions of years. Primordial black holes, whether they exist or not, force us to think about the universe differently. They force us to consider that the first permanent objects in the cosmos might not have been stars or gas clouds or anything made of ordinary matter in the familiar sense. They might have been black holes, pure gravity. Singularities wrapped in event horizons, formed in the chaos of the first instant and surviving unchanged through nearly 14 billion years of cosmic expansion. That is a strange idea. It violates our intuition about how things are supposed to be built. We expect simple things first, complex things later. Atoms, then molecules, then stars, then galaxies. A slow progression from the simple to the complex, with each layer depending on the one beneath it. But the early universe did not care about our expectations. It had gravity, it had density fluctuations, and it had time. From those ingredients, in a span of less than a second, it might have built the first black holes, and those black holes, if they are real, have been shaping the flow of matter and the formation of structure ever since. They might have seeded the supermassive black holes that anchor every large galaxy. They might be part of the dark matter that holds galaxies together and fills the space between them. They might have influenced the formation of the first stars by creating gravitational wells where gas could collapse faster than it otherwise would. And they might still be out there, scattered throughout the cosmos, invisible but present, waiting for us to develop the tools and the techniques needed to finally detect them. The legacy of primordial black holes, if they exist, is not just about the past, it is about the present. Every galaxy we see including our own, sits in a halo of dark matter. If even a fraction of that dark matter is made of primordial black holes, then some of those black holes are close, very close, within a few light years of the Sun, drifting through the galactic disk, passing near stars, occasionally tugging on planets with their gravity. They are not dangerous. The odds of a close encounter are vanishingly small, and even a direct pass through the solar system would produce only faint gravitational ripples. But they are there, in the background, invisible threads woven into the fabric of the galaxy, and they connect us to the beginning. Every atom in your body was forged in a star that lived billions of years ago. But the black holes, if they are primordial, were forged before the first star ever ignited. They are older than the atoms that make up your body, older than the Sun, older than the Earth, older than the galaxy. They are fossils from the first moment, relics of a time when the universe was so young that the concept of time itself barely had meaning. If we can detect them, if we can confirm their existence and measure their properties, we will have found a direct connection to the instant of creation. A window into the universe's first second, the moment when gravity began the work of building everything that came after. The search is not over. The hypothesis is still open. The constraints are tightening, but the windows have not closed, and the universe, patient as always, is waiting. Primordial black holes might be out there, scattered across the cosmos, holding the answers to some of the deepest questions we have asked. How did supermassive black holes form so early? What is dark matter made of? How did the first galaxies assemble so quickly? Why does the universe have the structure it has, with galaxies clustered in filaments and vast voids in between? Or they might not be out there. The searches might continue to come up empty, the constraints might keep tightening, and eventually we might have to accept that the early universe did not produce black holes in significant numbers before the first stars. That the supermassive black holes grew from stellar seeds and direct collapse. That dark matter is made of particles we have not found yet. That the mysteries we are trying to solve require different explanations, different physics, different ideas. But until we know for certain, the hypothesis remains on the table. Primordial black holes, the oldest objects in the universe, the first anchors, the seeds of supermassive black holes, the potential component of dark matter, the fossils of the Big Bang. If they are real, they are everywhere, hidden in plain darkness, shaping the cosmos in ways we are only beginning to understand. And if they are not real, the universe has found a different path to build its structures, one that we are still working to uncover. Either way, the answer will tell us something fundamental about how the cosmos works, about the conditions in the first instant after the Big Bang, about the role of gravity in shaping structure on the largest scales, about the connection between the quantum fluctuations that inflation left behind and the galaxies we see filling the sky today. The search for primordial black holes is not just a hunt for a single type of object. It is a search for the universe's origin story. The moment when chaos became structure, the moment when gravity first carved permanent objects out of the expanding plasma, the moment when the universe stopped being a featureless fog and started becoming something interesting. We are still looking. Still searching the data for the faint gravitational whispers, the subtle lensing effects, the rare gamma-ray flashes that would confirm they are out there. The universe has not given us a clear answer yet, but it has given us hints, tantalizing suggestions that something is missing from our understanding of the early cosmos. Observations that do not quite fit the standard models. Black holes that are too massive, too early, galaxies that formed too quickly, structures that assembled before the timeline says they should have. Each observation opens the door a little wider for primordial black holes to step through. And if they do exist, if the searches finally succeed and we confirm their presence, it will change everything. Not just our understanding of black holes, but our understanding of the universe itself. The story of how the cosmos began, how it grew, how it assembled the structures we see today. The role of the first instant, the first fluctuations, the first black holes, the connection between the beginning and everything that followed. The legacy of primordial black holes would stretch from the first second to the present day, from the smallest quantum ripples to the largest supermassive monsters, from the invisible dark matter halos to the glowing galaxies they anchor. It would be a legacy written into the fabric of space-time itself, carved out in the first breath of creation and preserved unchanged through nearly 14 billion years of cosmic history. That is what is at stake. That is why the search matters. Not because primordial black holes are exotic or interesting, though they are both, but because they might be the key that unlocks the universe's earliest secrets, the connection between the quantum and the cosmic, the bridge between the first instant and the structures we see today, the fossils that tell us how it all began. If we can find them, if we can prove they are real, we will have answered one of the oldest questions humanity has ever asked. Where did everything come from? And the answer, strange as it sounds, might be that it came from black holes. Black holes that formed before stars, before atoms, before light itself had a chance to travel freely through space. Black holes that have been waiting in the dark ever since, silent and patient, holding the story of creation in the curvature of space around their event horizons. All we have to do is learn how to read it. We started with a pulse, a faint tick buried in the seismic record of the Earth, repeating every 26 seconds, refusing to explain itself. We ended 13.8 billion years in the past, standing at the edge of a universe so young that stars had not yet ignited, staring at black holes that might have formed before anything else. That gap between the mysteries we can measure today and the ones we can only infer from the light of distant galaxies is where this story lives. Primordial black holes are not proven, they might not exist. 50 years of searching has tightened the constraints, closed some doors, left others open. But the hypothesis refuses to die because the observations refuse to cooperate. Supermassive black holes that formed too early, galaxies that assembled too quickly, dark matter that fills 85% of the universe and has never been directly detected, gravitational wave signals from merging black holes heavier than stellar models comfortably predict. Each mystery alone can be explained with enough creativity. Together, they point towards something missing. A population of objects formed in the first instant, seeded the first structures, and have been drifting through space ever since. Invisible anchors shaping the flow of matter across billions of light years. If primordial black holes are real, they are older than stars, older than atoms, older than light itself. Fossils from a moment when the universe was too young to have rules, carved out by gravity acting on quantum noise, stretched to cosmic scales. If they are not real, the universe found a different way to build its monsters, and the timeline problem remains unsolved. Either way, the answer is out there, somewhere in the dark, between the stars, woven into the fabric of galaxies, waiting for the right instrument to finally catch a glimpse. The universe has been patient for 13.8 billion years. It can wait a little longer. As new observatories listen deeper into cosmic dawn, the next clue may not reveal one first black hole, but reveal how beginnings endure,